Is faster-than-light travel possible? It's a question that sparks the imagination and challenges the boundaries of modern physics. In science fiction, we see spaceships zipping across the galaxy at speeds that dwarf light. But what does science have to say about this? First, let's clarify what faster-than-light, or FTL travel, actually means. Essentially, it refers to any method of travel that exceeds the speed at which light travels through space. Light speed is roughly 299,792 kilometers per second, a speed that has long been considered the universal speed limit. To understand why FTL travel is such a fascinating topic, we need to delve into the basics of light speed. Light speed has been a cornerstone of physics since its measurement in the 19th century, and it plays a crucial role in our understanding of space and time. Einstein's theory of relativity revolutionized our understanding of light speed, introducing concepts like time dilation and mass increase at high velocities. According to this theory, as objects approach the speed of light, their mass effectively increases, making it impossible for them to reach or exceed light speed. This brings us to the theoretical concepts of FTL travel. Ideas like the warp drive, wormholes, and tachyons offer intriguing possibilities for overcoming the light speed barrier. A warp drive, for instance, could theoretically bend space-time to allow faster-than-light travel without actually moving faster than light within a local region. However, these theoretical concepts are not without their challenges and paradoxes. Issues like causality violations, the requirement of infinite energy, and the need for exotic matter make FTL travel a highly speculative endeavor. Current scientific research continues to explore the possibilities and limitations of FTL travel. From NASA's investigations into warp drives to experiments in quantum mechanics, scientists are actively searching for ways to make FTL a reality, or at the very least, understand its implications. Yet, there are alternative theories that argue FTL travel might be fundamentally impossible. These theories challenge the feasibility of breaking the light speed barrier and suggest that our current understanding of physics might be incomplete or flawed. Science fiction has long embraced the concept of FTL travel, often depicting it in imaginative and visually stunning ways. This genre not only entertains but also inspires real scientific inquiry, pushing the boundaries of what might be achievable. As we dive into the science and speculation surrounding FTL travel, it's important to consider both the theoretical possibilities and the practical limitations. The question of whether FTL travel is within humanity's grasp continues to inspire both scientists and dreamers alike. The speed of light is a fundamental constant in physics, represented as approximately 299,792 kilometers per second, or about 186,282 miles per second. It's the fastest speed at which information or matter can travel through the vacuum of space. This speed was first measured in the 1670s by Danish astronomer Ole Rømer, who observed the motion of Jupiter's moon, Io. Rømer's work provided the first quantitative estimate of light speed, though it would take centuries for more precise measurements to be made. The value of the speed of light is not just a number, it's a cornerstone of modern physics. It plays a critical role in the theory of relativity, shaping our understanding of space, time, and energy. In the context of Einstein's theory of relativity, the speed of light is not just a limit but a constant that applies universally. Whether you're moving toward or away from a light source, the speed of light remains the same, which defies our everyday experiences with speed and motion. This constancy of light speed is what makes it so significant in the field of relativity. It serves as the foundation for the concept that nothing can exceed or even reach this speed without encountering insurmountable challenges. Light speed is also integral to the way we measure distances in space. Astronomers use light years to describe the vast distances between celestial objects, with 1 light year being the distance that light travels in 1 year, roughly 9.46 trillion kilometers or 5.88 trillion miles. The speed of light has practical applications beyond theoretical physics. It affects technologies such as GPS and communication systems, which rely on precise timing and signal propagation to function effectively. Researchers have conducted numerous experiments to verify the speed of light, from measuring its passage through various mediums to using lasers and advanced equipment. These experiments continually affirm the speed of light as a stable and unchanging constant. Understanding the speed of light also involves acknowledging its behavior in different environments. When light passes through materials like glass or water, it slows down compared to its speed in a vacuum, which affects how we perceive it. The value of the speed of light is so fundamental that it's used as a standard in defining other physical constants and units of measurement. The meter, for instance, is defined based on the distance light travels in a specified fraction of a second. Given its central role in our understanding of the universe, any theories proposing faster than light travel must contend with this constant. The speed of light sets a boundary that any proposed FTL methods must navigate or overcome. The concept of light speed is also tied to the idea of causality, which is the principle that cause precedes effect. If something were to travel faster than light, it could theoretically lead to situations where events appear to happen out of sequence. In essence, the speed of light represents a limit that defines the structure of spacetime. It's a speed that integrates into our fundamental theories of physics, influencing everything from the fabric of spacetime to the propagation of electromagnetic waves. As we explore the possibility of FTL travel, understanding the speed of light helps frame the challenges and limitations we face. It's not just a number, but a profound element of our physical reality that shapes our approach to space travel. The constancy of light speed also suggests that if FTL travel were possible, it might require entirely new physics or a revolutionary understanding of spacetime. Current theories and experiments focus on working within the constraints established by this fundamental constant. The measurement of light speed began in the 1670s with Danish astronomer Ole Rømer. He made his observations by studying the motion of Jupiter's moon Io, noting that its eclipses appeared to vary depending on Earth's position relative to Jupiter. Rømer discovered that the time between these eclipses changed as Earth moved closer to or farther from Jupiter, leading him to conclude that light had a finite speed. His findings suggested that light traveled at a measurable speed, though his estimate was not precise by today's standards. In the early 19th century, French physicist Hippolyte Fizeau refined the measurement of light speed using a rotating mirror experiment. Fizeau's method involved reflecting light off a rotating mirror and measuring the time it took for the light to travel to a distant mirror and back. Fizeau's experiment provided a more accurate value for the speed of light, approximately 313,000 kilometers per second, which was remarkably close to the modern value. His work was a major breakthrough in understanding the speed at which light travels. Later, in 1862, French physicist Armand Fizeau's colleague Léon Foucault improved upon this by using a rotating disk. Foucault's method involved reflecting light between rotating mirrors and measuring the shift in the reflected beam, which provided a more precise measurement. Foucault's measurements reduced the speed of light estimate to around 298,000 kilometers per second, which was closer to the current accepted value. His work demonstrated the effectiveness of the rotating mirror technique in measuring light speed accurately. These early experiments were crucial in laying the groundwork for modern physics. They showed that light speed is a finite quantity and provided a basis for further research into the nature of light and its role in the universe. In the 20th century, advancements in technology allowed for even more precise measurements of light speed. The advent of laser technology and advanced timing instruments enabled scientists to refine their estimates to the incredibly precise value we use today. Modern measurements of light speed are performed using techniques such as laser interferometry, which involves splitting and recombining light beams to measure their speed with high accuracy. These methods have confirmed the speed of light to be approximately 299,792 kilometers per second in a vacuum. The precision of current light speed measurements is essential for various fields, including telecommunications, GPS, and fundamental physics research. It allows scientists to test theories and conduct experiments with a high degree of accuracy. Each advancement in measuring light speed has contributed to our understanding of fundamental physical laws. From early astronomical observations to sophisticated laboratory techniques, these efforts have shaped our comprehension of light's role in the universe. These historical measurements not only provided key insights into light's behavior, but also influenced subsequent developments in physics. They helped establish the speed of light as a critical constant in our scientific theories and technological applications. As we explore the possibilities of faster-than-light travel, understanding the history of light speed measurements helps us appreciate the precision required to test such theories. It also underscores the challenges faced when attempting to exceed this fundamental limit. The progress from Romer's initial observations to contemporary measurements reflects the evolution of scientific methods and technology. Each step in this journey has expanded our knowledge and refined our understanding of light and its speed. These historical milestones are more than just dates and experiments. They represent significant strides in science that continue to influence our quest to explore the boundaries of physical laws. The accurate measurement of light speed remains a cornerstone of modern physics. Light speed holds a central place in physics as a universal constant that influences many aspects of our understanding of the universe. It's integral to Einstein's theory of relativity, which reshaped our concepts of space and time. In relativity, light speed is not just a measure of how fast light travels, but it's also the maximum speed at which information or energy can be transmitted. This principle establishes a fundamental limit on the speed of any physical object or signal. The constancy of light speed leads to the concept of spacetime, where space and time are intertwined into a four-dimensional fabric. This framework shows that as an object approaches light speed, both space and time undergo significant changes. Light speed also affects our perception of time, known as time dilation. According to relativity, time slows down for objects moving at speeds close to that of light, which has profound implications for high-speed space travel and particle physics. Additionally, light speed is crucial for understanding the relationship between energy and mass. Einstein's famous equation, E = mc2, uses light speed to describe how energy and mass are interchangeable, highlighting the immense energy contained in even small amounts of matter. In cosmology, the speed of light serves as a cosmic speed limit, shaping our understanding of the observable universe. It determines how far we can see and how we interpret the light reaching us from distant stars and galaxies. The concept of light speed also influences the design and functionality of modern technologies. GPS systems, for example, rely on precise timing and signal propagation, which are directly linked to the speed at which light travels. Light speed is fundamental in defining the meter, the standard unit of length in the International System of Units. This definition is based on the distance light travels in a vacuum in a specific fraction of a second, underscoring its role in measurement standards. In theoretical physics, the idea of light speed sets the stage for discussions about faster-than-light travel and communication. Any proposed methods for surpassing this limit must contend with the implications and constraints imposed by this fundamental constant. The speed of light also impacts our understanding of fundamental forces and particles. For instance, the behavior of electromagnetic fields and the propagation of electromagnetic waves are described in terms of light speed, linking it to the nature of electric and magnetic interactions. Understanding light speed helps scientists explore the boundaries of physical theories and test their predictions. It provides a benchmark against which new theories and experimental results are measured, ensuring consistency with established physics. In particle physics, the speed of light plays a key role in the equations governing particle behavior. High-energy particles often approach light speed, and their interactions are described using relativistic principles that incorporate this constant. Light speed also plays a role in our comprehension of gravitational effects. General relativity predicts that changes in gravitational fields propagate at the speed of light, influencing how we understand phenomena such as black holes and gravitational waves. In essence, the significance of light speed extends beyond mere measurement. It underpins much of modern physics and our interpretation of the universe. Its constancy and role in various equations and theories make it a cornerstone of scientific understanding. As we continue to explore the frontiers of physics, the speed of light remains a crucial factor in testing theories and pushing the boundaries of what is possible. It is a constant that continually challenges and refines our understanding of the cosmos. Einstein's theory of relativity fundamentally altered our understanding of space and time, with light speed playing a pivotal role. According to relativity, the speed of light is a constant in all inertial frames of reference, meaning it remains the same regardless of the observer's motion. Special relativity, introduced in 1905, is built around the idea that light speed is the ultimate speed limit. This theory demonstrates that as an object moves closer to light speed, its mass effectively increases and time slows down relative to a stationary observer. One of the key concepts in special relativity is time dilation, where time appears to move slower for objects traveling at speeds near that of light. This effect has been experimentally confirmed using atomic clocks on fast-moving jets and satellites. Another consequence of relativity is length contraction, where objects appear shorter in the direction of motion as they approach light speed. This means that distances in the direction of travel shrink for objects moving at high velocities relative to a stationary observer. General relativity, introduced in 1915, extends these principles to include gravity. In this theory, light speed is crucial in describing how massive objects warp the fabric of spacetime, creating what we perceive as gravity. The theory predicts that gravitational waves, ripples in spacetime caused by accelerating masses, travel at the speed of light. This prediction was confirmed by the observation of gravitational waves from colliding black holes in 2015, validating Einstein's theory. Einstein's equation, E=mc2, shows the relationship between energy and mass, with light speed as the conversion factor. This equation highlights how a small amount of mass can be converted into a vast amount of energy, explaining processes such as nuclear reactions. Special relativity also introduces the concept of spacetime, a four-dimensional continuum where space and time are intertwined. The speed of light acts as a bridge between these dimensions, influencing how events are measured and perceived. In relativistic physics, the idea that nothing can exceed light speed sets a limit on the maximum speed of information transfer. This principle affects our understanding of causality, ensuring that cause precedes effect in all inertial frames. Relativity challenges our intuitive notions of time and space by showing that they are not absolute, but relative to the observer's frame of reference. Light speed is central to these revelations, defining how measurements of time and distance change with velocity. General relativity's description of black holes and the bending of light around massive objects relies on the constancy of light speed. The theory predicts phenomena such as gravitational lensing, where light is bent by the gravity of distant objects. The idea that light speed is a universal constant underpins the entire framework of relativity. This principle ensures that the laws of physics remain consistent for all observers, regardless of their relative motion or position in the universe. Relativity also has practical implications for modern technology, such as GPS systems. These systems account for relativistic effects due to the high speeds of satellites and their position relative to Earth's gravitational field, ensuring accurate positioning. Einstein's theories have led to numerous experimental tests that validate the role of light speed. From particle accelerators to satellite measurements, these experiments confirm the predictions of relativity and the constancy of light speed. The interplay between light speed and relativity has profound implications for our understanding of the universe. It sets the stage for exploring advanced concepts like black holes, quantum mechanics, and the nature of space-time itself. As we investigate the possibilities of faster-than-light travel, the principles of relativity serve as a crucial framework. Any proposed methods for exceeding light speed must address the constraints and predictions established by Einstein's groundbreaking work. The concept of a universal speed limit is a fundamental idea in modern physics, established by Einstein's theory of relativity. This speed limit is defined by the speed of light, which sets the maximum rate at which information or matter can travel through space. According to relativity, as an object approaches the speed of light, its energy and momentum increase dramatically. This leads to the requirement of infinite energy to reach or exceed light speed, making it practically impossible for any object with mass. The universal speed limit ensures that causality is preserved throughout the universe. By preventing objects from traveling faster than light, the theory maintains that cause and effect relationships remain consistent and predictable. This speed limit also influences the nature of spacetime, where distances and times are interrelated. The constant speed of light means that any movement through space affects the passage of time, demonstrating the inseparable connection between space and time. In theoretical physics, the idea of a universal speed limit challenges concepts like faster-than-light travel and communication. Proposals, such as warp drives or wormholes, must work within the constraints of this speed limit or find ways to circumvent it. The speed of light as a limit also impacts our understanding of the observable universe. It defines the boundaries of the observable cosmos, as light from distant objects takes time to reach us, limiting how far we can see. Efforts to surpass this universal speed limit often involve speculative concepts like exotic matter or hypothetical particles. These ideas attempt to bypass the speed limit by manipulating spacetime itself rather than exceeding light speed directly. Quantum mechanics introduces phenomena such as entanglement, which might seem to challenge the speed limit. However, quantum entanglement does not involve the transfer of information faster than light, but rather an instantaneous correlation between entangled particles. Relativity's universal speed limit is also a critical component of modern technology, including telecommunications and GPS systems. These systems rely on the consistent propagation of signals and must account for relativistic effects to function accurately. The concept of a universal speed limit has far-reaching implications for the future of space exploration. It shapes the design of spacecraft and propulsion systems, as engineers must consider how to operate within the constraints of light speed. Understanding the universal speed limit helps frame our expectations for future technological advances. While achieving or surpassing light speed remains speculative, it's essential to base new theories and experiments on the established limits of physics. Attempts to break the speed limit often lead to new insights into the nature of physics. The process of exploring these possibilities can reveal more about the fundamental principles governing space, time, and energy. The universal speed limit also provides a reference point for measuring and comparing different speeds and energies. It serves as a constant against which other physical phenomena are evaluated and understood. In essence, the concept of a universal speed limit underscores the challenges of achieving faster-than-light travel. It remains a cornerstone of our understanding of the physical universe and the constraints imposed by our current theories. As we explore the frontiers of physics, the speed of light will continue to be a critical factor in evaluating new ideas and technologies. Its role as a universal constant ensures that any advances in our understanding of space and time must align with this fundamental principle. The ongoing quest to understand and potentially overcome the universal speed limit reflects the dynamic nature of scientific inquiry. It challenges scientists to develop new theories and technologies while adhering to the established framework of relativity and light speed. Special relativity, introduced by Einstein in 1905, revolutionized our understanding of space and time. It is based on two key postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light is constant in all inertial frames of reference. One of the central ideas of special relativity is time dilation, where time slows down for objects moving at high speeds relative to a stationary observer. This effect has been experimentally confirmed with precision, showing that time passes differently depending on velocity. Length contraction is another consequence of special relativity, where objects appear shorter in the direction of motion when traveling close to the speed of light. This phenomenon affects our perception of space for fast-moving objects relative to an observer. Special relativity also introduces the concept of simultaneity, which suggests that events that occur simultaneously for one observer may not be simultaneous for another moving at a different velocity. This challenges our intuitive notions of time and space. The theory demonstrates that mass and energy are interchangeable, encapsulated in Einstein's famous equation, E=mc². This equation highlights how a small amount of mass can be converted into a large amount of energy, underpinning nuclear reactions and particle physics. In special relativity, the speed of light serves as a universal constant that affects how we understand motion and energy. The theory implies that no object with mass can reach or exceed the speed of light, establishing a fundamental limit. Special relativity leads to the concept of spacetime, a four-dimensional continuum where space and time are interconnected. This framework reshapes our understanding of the universe, showing that events are described by both spatial and temporal coordinates. The theory also impacts our understanding of momentum and energy, introducing relativistic formulas that adjust for high velocities. These adjustments are crucial for accurately describing the behavior of particles in high-energy physics. Experimental evidence supporting special relativity includes observations of particle accelerators and atomic clocks, which show that time dilation and length contraction occur as predicted. These experiments confirm the accuracy of the theory in practical scenarios. Special relativity has practical implications for modern technology, such as GPS systems, which must account for relativistic effects due to the high speeds and gravitational influences on satellites. These corrections ensure accurate positioning and timing. The theory also addresses the relativity of simultaneity, showing that the order of events can differ depending on the observer's frame of reference. This insight into how different observers perceive events adds depth to our understanding of temporal relationships. Special relativity challenges classical physics by demonstrating that space and time are not absolute but relative to the observer's state of motion. This shift in perspective has profound implications for both theoretical and experimental physics. The equations of special relativity have been tested and confirmed through numerous experiments, reinforcing the theory's predictions about time dilation, length contraction, and the relationship between mass and energy. These confirmations validate Einstein's groundbreaking work. Special relativity also impacts our understanding of energy and momentum in high-speed collisions, where relativistic effects become significant. This has implications for research in particle physics and cosmic phenomena. The theory reshapes our conceptual framework for understanding the universe, emphasizing the importance of the observer's motion in defining physical laws. It provides a new lens through which to view the interactions of matter and energy. Special relativity's principles extend beyond theoretical physics, influencing fields such as cosmology, where they help describe the behavior of objects moving at significant fractions of light speed. The theory remains a cornerstone of modern scientific understanding. Time dilation is a phenomenon predicted by Einstein's theory of relativity, where time slows down for objects moving at speeds close to the speed of light. This effect becomes more pronounced as the object's velocity increases relative to a stationary observer. For example, if astronauts travel at near-light speeds, they would experience less passage of time compared to people on Earth. This means that while years might pass for those on Earth, only a few months could elapse for the astronauts on their journey. The degree of time dilation can be calculated using the Lorentz factor, which is derived from the speed of the moving object. The factor grows larger as the object's speed approaches the speed of light, causing a greater discrepancy in time experienced by different observers. Experimental evidence for time dilation comes from observations with high-speed particles, such as muons. These particles, traveling close to light speed, decay more slowly than stationary muons, confirming the effects predicted by relativity. Atomic clocks flown on fast-moving jets have also demonstrated time dilation. When compared with clocks that remain on the ground, those on the jet show a slight lag, consistent with the predictions of special relativity. Time dilation has practical implications for systems involving high-speed travel, such as satellites. The synchronization of clocks in GPS satellites must account for time dilation effects due to their high speeds and lower gravitational field compared to Earth. In particle accelerators, particles are accelerated to speeds close to light, experiencing significant time dilation. This allows physicists to study particles with very short lifespans, as the time dilation effectively extends their observable life. The concept of time dilation also plays a crucial role in science fiction scenarios involving high-speed space travel. It offers a fascinating way to explore the effects of traveling close to light speed on the passage of time. Time dilation challenges our intuitive understanding of time as a constant, absolute measure. Instead, it reveals that time is relative and can vary depending on an object's speed and gravitational influences. The effects of time dilation are symmetrical. Both the moving observer and the stationary observer would see each other's clocks running slower. This reciprocal nature emphasizes the relativity of time and how it depends on the observer's frame of reference. In practical applications such as designing high-speed spacecraft, engineers must consider time dilation to accurately predict the effects on crew members and mission timelines. This consideration is essential for future space travel endeavors. Time dilation also influences our understanding of aging and lifespan in the context of relativistic travel. For astronauts traveling at high velocities, the relativistic effects could result in them aging more slowly compared to those remaining on Earth. In the realm of theoretical physics, time dilation opens discussions about the possibility of traveling to distant stars within a human lifetime. It provides a basis for exploring advanced propulsion methods and their impact on time experienced by travelers. The relativistic equations governing time dilation have been thoroughly tested through experiments and observations. These tests continue to affirm the theory's accuracy and its alignment with observed phenomena. Time dilation is not just a theoretical concept, but a real effect that has been measured and verified in various scientific experiments. Its implications extend to many areas of physics and technology, underscoring the practical importance of relativity. The phenomenon of time dilation adds depth to our understanding of the universe by showing that time is not an absolute constant, but a flexible dimension affected by speed. This insight continues to influence both theoretical and applied physics. At relativistic speeds, an object's mass increases according to Einstein's theory of relativity. This effect, known as relativistic mass increase, becomes more pronounced as the object's velocity approaches the speed of light. The increase in mass is described by the Lorentz factor, which adjusts the object's mass based on its velocity. As the speed gets closer to light speed, the Lorentz factor grows, leading to a substantial increase in the object's relativistic mass. Relativistic mass increase has significant implications for high-speed travel and particle physics. For instance, particles in accelerators, moving at velocities close to light speed, experience a dramatic rise in mass, affecting their interactions and energy levels. This mass increase means that more energy is required to further accelerate an object as it approaches light speed. The energy required grows exponentially, making it increasingly difficult to achieve or exceed the speed of light. In practical terms, the concept of mass increase impacts the design of particle accelerators. Engineers must account for the rising mass of particles to ensure they have enough energy to accelerate them to desired velocities. Relativistic mass is different from rest mass, which remains constant regardless of velocity. The concept of relativistic mass helps describe the effects of high-speed motion, but is often replaced by the idea of energy and momentum in modern physics. The increase in mass at high speeds also influences the gravitational effects of fast-moving objects. According to relativity, the increased mass affects how these objects interact with gravitational fields, leading to modifications in their orbits and trajectories. Observations of high-energy cosmic particles provide evidence for relativistic mass increase. These particles, moving at near-light speeds, exhibit properties consistent with the predicted rise in mass as their velocities increase. In theoretical discussions, relativistic mass highlights the limits of classical mechanics and the necessity of relativistic corrections. It shows that our understanding of mass and energy must be adjusted when dealing with speeds approaching light. The concept of mass increase is essential for understanding high-energy astrophysical phenomena, such as supernovae and black hole accretion disks. These phenomena involve objects moving at relativistic speeds where mass effects play a crucial role. Relativistic mass also impacts the behavior of objects in high-speed collisions. The increased mass affects how these objects interact, leading to new physics phenomena that are explored in high-energy physics experiments. As particles move faster, their relativistic mass grows, which influences their energy and momentum. This relationship is central to the study of fundamental forces and interactions in particle physics. The idea of relativistic mass increase underscores the importance of relativity in understanding the universe. It demonstrates how classical concepts need to be revised to account for the effects of high-speed motion. In the context of space travel, relativistic mass increase presents challenges for accelerating spacecraft to high velocities. The increasing mass requires exponentially more energy, making near-light-speed travel a daunting engineering problem. Relativistic mass has been experimentally verified through observations in particle accelerators and cosmic rays. These experiments confirm that mass increases according to the predictions of relativity, validating the theory's impact on high-speed physics. The effects of relativistic mass illustrate how relativity reshapes our understanding of fundamental physical concepts. It challenges traditional notions of mass and energy, providing a more accurate description of high-speed dynamics. Spacetime is a fundamental concept in Einstein's theory of relativity that combines the three dimensions of space with the dimension of time into a four-dimensional continuum. This integrated framework allows us to understand how objects and events are interconnected in a unified model. In spacetime, the traditional view of space and time as separate entities is replaced by a unified fabric that can be warped and curved by the presence of mass and energy. This curvature affects the motion of objects, explaining gravitational effects as a result of this warping. One key aspect of spacetime is that it allows for the description of how gravity works in terms of geometry. Massive objects like stars and planets create curves in spacetime that influence the trajectory of other objects, causing what we perceive as gravitational attraction. The curvature of spacetime is not just a theoretical concept, but has been observed in phenomena such as gravitational lensing. This effect occurs when light from distant stars is bent around massive objects, confirming the predictions of general relativity. Events in spacetime are described by coordinates that include both spatial and temporal dimensions. This four-dimensional coordinate system helps in understanding how events are positioned and how they relate to each other in time and space. Spacetime also introduces the idea that the passage of time can vary depending on an object's position within a gravitational field. This means that time runs slower in stronger gravitational fields, a phenomenon known as gravitational time dilation. The concept of spacetime is essential for understanding the behavior of objects moving at high speeds or in strong gravitational fields. It provides a framework for analyzing how these conditions affect the passage of time and the geometry of space. In everyday experiences, spacetime effects are subtle and not noticeable due to our relatively low speeds and weak gravitational fields. However, at high speeds or in the presence of strong gravitational forces, spacetime effects become more pronounced and observable. Spacetime can be visualized as a flexible sheet that bends in response to mass and energy. This analogy helps illustrate how objects follow curved paths in response to the distortions in this fabric, akin to how a marble rolls along a warped sheet. The idea of spacetime challenges classical physics by showing that time and space are not fixed, but can change depending on the observer's motion and gravitational field. This shift in perspective has profound implications for how we understand the universe. The interactions between objects in spacetime are described by the equations of general relativity, which account for the effects of gravity on the curvature of spacetime. These equations help predict the behavior of celestial bodies and the propagation of light. Spacetime also plays a role in understanding the expansion of the universe. The fabric of spacetime itself stretches, leading to the observed phenomenon of cosmic expansion and the redshift of distant galaxies. In theoretical physics, spacetime provides a framework for exploring advanced concepts such as wormholes and time travel. These speculative ideas involve manipulating the fabric of spacetime to achieve effects that defy our everyday experiences. The concept of spacetime has been validated through numerous experiments and observations, including the detection of gravitational waves. These waves, ripples in the fabric of spacetime, confirm the predictions made by Einstein's theory. Spacetime fundamentally reshapes our understanding of gravity, moving away from the idea of forces acting at a distance to a model where gravity is a consequence of spacetime curvature. This paradigm shift has been essential in modern physics. As we explore the universe and test theories, spacetime remains a central concept that helps explain both everyday phenomena and extreme conditions. It provides a cohesive framework for understanding how space and time are interrelated in the context of physical laws. Light speed is considered the cosmic speed limit due to its fundamental role in the fabric of spacetime. According to Einstein's theory of relativity, the speed of light is the maximum speed at which information or matter can travel through the universe. The constancy of light speed means that it remains the same for all observers, regardless of their relative motion. This universality establishes a speed limit, because it sets a fundamental constraint on how fast anything can move or communicate. As objects approach the speed of light, their energy and momentum increase dramatically. This exponential growth means that achieving or surpassing light speed would require an infinite amount of energy, which is not feasible with our current understanding and technology. The speed of light also affects how we perceive space and time. At high velocities, time dilation and length contraction occur, demonstrating that the nature of time and space is intertwined with the speed of light as a universal constant. The cosmic speed limit is crucial for maintaining causality, ensuring that cause and effect relationships are preserved. Allowing faster-than-light travel would violate this principle, leading to paradoxes and inconsistencies in the sequence of events. Special relativity shows that no object with mass can reach or exceed the speed of light. As an object accelerates, its mass increases, requiring ever more energy to continue accelerating, making light speed an unattainable boundary for massive objects. The concept of light speed as a limit is also supported by the observed behavior of particles and signals. Experiments with high-energy particles and electromagnetic waves consistently align with the predictions of relativity, reinforcing the idea of light speed as a cosmic speed limit. In addition to its role in relativity, light speed affects our understanding of the observable universe. It determines how far we can see and how long it takes for light from distant objects to reach us, defining the boundaries of our cosmic horizon. Attempts to exceed light speed often involve speculative theories, such as warp drives or tachyons. These concepts seek to bypass the speed limit by altering spacetime or proposing hypothetical particles, but they remain unconfirmed by empirical evidence. The speed of light influences various physical laws and constants, integrating them into a coherent framework. Its role as a cosmic speed limit ensures that these laws apply consistently across different frames of reference and conditions. Faster-than-light travel would require new physics beyond our current theories, challenging the well-established principles of relativity. The pursuit of such technologies would need to reconcile with the constraints imposed by the cosmic speed limit. In cosmology, the speed of light sets limits on how quickly the universe can expand and how information can propagate across vast distances. This affects our understanding of the universe's growth and the distribution of galaxies. Understanding light speed as a limit also impacts theoretical models of the universe, such as those involving black holes and the Big Bang. These models rely on the assumption that light speed is a constant boundary, shaping our comprehension of extreme cosmic phenomena. The concept of light speed as a speed limit has practical implications for space exploration and communication. It sets constraints on the design and operation of spacecraft and communication systems, influencing how we plan interstellar missions. In summary, light speed serves as a universal constant that defines the maximum speed for all physical processes. Its role as a cosmic speed limit underpins the structure of relativity and the laws of physics that govern the behavior of matter and energy. A warp drive is a theoretical propulsion system that aims to achieve faster-than-light travel by manipulating spacetime itself. Unlike conventional propulsion methods, a warp drive would not move a spacecraft through space, but would instead alter the fabric of spacetime to allow it to travel faster than light. The concept of a warp drive was popularized by physicist Miguel Alcubierre in 1994, who proposed a model where a spacecraft could be enclosed in a warp bubble. This bubble would contract space in front of the spacecraft and expand it behind, effectively moving the craft faster than light relative to an external observer. In the Alcubierre drive model, the warp bubble would allow the spacecraft to traverse vast distances in a relatively short time without locally breaking the speed of light. This approach circumvents the limitations imposed by relativity by not exceeding light speed within the bubble itself. The theoretical framework for a warp drive relies on the principles of general relativity and exotic matter with negative energy density. This exotic matter would be required to create and sustain the warp bubble, but such matter has not been observed or confirmed. The idea of a warp drive raises intriguing possibilities for interstellar travel, potentially allowing humans to explore distant stars within a human lifetime. However, the feasibility of constructing and operating a warp drive remains highly speculative and faces significant theoretical and practical challenges. Challenges to the warp drive concept include the need for enormous amounts of energy and the question of whether exotic matter can actually exist. Current estimates suggest that the energy required could be on the order of the mass energy of planets or stars. Despite these challenges, the warp drive concept continues to be a subject of interest in theoretical physics and science fiction. It offers a framework for imagining how future technologies might overcome the cosmic speed limit and explore new frontiers. The warp drive idea also intersects with discussions about wormholes and other speculative methods of faster-than-light travel. Both concepts share the goal of circumventing the speed limit imposed by relativity, but through different mechanisms. Researchers have explored various extensions and modifications to the original warp drive model, seeking ways to reduce energy requirements or address theoretical issues. These modifications aim to make the concept more viable or align it with emerging scientific discoveries. Although no experimental evidence supports the existence of warp drives or exotic matter, ongoing research into the nature of spacetime and energy may provide new insights. Advances in fundamental physics could potentially offer pathways to realizing such speculative ideas. The warp drive remains a powerful tool for sparking imagination and advancing discussions about the future of space travel. It serves as a hypothetical framework that challenges our understanding of physics and encourages innovative thinking about the universe. The theoretical exploration of warp drives also prompts discussions about the potential impact on our understanding of fundamental physical laws. Any breakthroughs in this area could lead to profound changes in how we perceive and interact with space-time. In addition to scientific interest, the warp drive concept has inspired numerous works of science fiction, including popular franchises. These fictional portrayals contribute to public interest and imagination about the possibilities of advanced space travel technologies. The study of warp drives involves a multidisciplinary approach, incorporating insights from physics, engineering, and cosmology. This collaborative effort aims to address the many questions and challenges associated with developing such advanced technologies. Even if practical warp drives remain far from realization, the theoretical exploration contributes to our broader understanding of the universe. It encourages the examination of fundamental concepts and the pursuit of innovative solutions to complex scientific problems. In summary, the warp drive represents a fascinating and ambitious idea for achieving faster-than-light travel by manipulating space-time. While its practicality is still uncertain, it serves as a stimulating concept for both scientific inquiry and speculative fiction. Wormholes are theoretical tunnels or shortcuts through space-time that could connect distant regions of the universe. These structures are often visualized as a bridge with two ends at different points in space-time, potentially allowing for instant travel between them. The concept of a wormhole is rooted in the equations of general relativity, which allow for such solutions under certain conditions. Wormholes are predicted to form if space-time is curved in specific ways, though their actual existence remains unproven. In a typical wormhole model, one end of the wormhole is called the mouth, and the other end is the throat. The throat connects the two mouths, providing a pathway that could, in theory, allow for rapid travel between them. The idea of wormholes raises intriguing possibilities for interstellar travel, as they could potentially bypass the vast distances between stars. This concept has been popularized in science fiction as a means of achieving faster-than-light travel or exploring distant galaxies. To function as a viable means of travel, a wormhole would need to remain stable and traversable. However, current theories suggest that stabilizing a wormhole would require exotic matter with negative energy density, which has yet to be observed or understood. One challenge associated with wormholes is the potential for time travel paradoxes. If a wormhole allows for travel back in time, it could lead to causal inconsistencies, such as the famous grandfather paradox, where events might contradict themselves. Wormholes could be classified into different types based on their properties. For example, traversable wormholes are those that could potentially be used for travel, while others might be non-traversable or only theoretical. Theoretical models of wormholes suggest that they could be either static or dynamic. A static wormhole remains open at all times, while a dynamic wormhole might fluctuate, potentially opening and closing in response to external conditions. Current research into wormholes includes exploring how they might be detected or created. This involves studying their effects on light and matter, which could provide indirect evidence of their existence if they were to be observed. The stability of wormholes is a major topic of investigation. Without a stable structure, a wormhole could collapse or close before anything could pass through, limiting its practical use for travel. In addition to their theoretical implications, wormholes challenge our understanding of fundamental physics. They require rethinking concepts such as causality, energy, and the nature of space-time itself. Wormholes also intersect with discussions about the potential for faster-than-light communication. If wormholes could be harnessed, they might offer a way to send information across vast distances instantly. The study of wormholes is ongoing and speculative, with many theoretical models proposing different ways to approach or utilize these structures. Research continues to explore whether such phenomena could be real and how they might be applied. Exploring wormholes involves a multidisciplinary approach, integrating insights from physics, mathematics, and cosmology. This collaboration aims to address the many theoretical challenges and questions associated with wormhole theory. Despite their speculative nature, wormholes provide a stimulating framework for exploring the possibilities of advanced physics. They offer a way to question and expand our understanding of the universe. In summary, wormholes represent a fascinating theoretical concept that suggests pathways through space-time could exist, potentially revolutionizing our approach to travel and communication across cosmic distances. Their study encourages continued investigation into the nature of spacetime and fundamental physics. Tachyons are hypothetical particles that are theorized to travel faster than the speed of light. These particles arise from solutions to the equations of relativity, suggesting that if they exist, they could exceed the cosmic speed limit. The concept of tachyons was first proposed in the early 20th century, with the idea that they might possess imaginary mass. This imaginary mass would allow tachyons to move faster than light, as opposed to ordinary particles which require infinite energy to reach light speed. One intriguing aspect of tachyons is their potential implications for causality and time travel. If tachyons can travel faster than light, they could theoretically allow for information or objects to be sent backward in time, creating paradoxes that challenge our understanding of cause and effect. Despite their theoretical existence, tachyons have not been observed experimentally. Their presence would require detecting particles that move faster than light, which has proven elusive with current technology and understanding of particle physics. Tachyons would be expected to have very different properties compared to regular particles. For instance, they would exhibit reversed causality effects and possibly have unusual interactions with other matter and energy. The study of tachyons also intersects with discussions about the nature of spacetime. Their existence would challenge the conventional views of spacetime structure, requiring a re-evaluation of fundamental principles in physics. If tachyons were discovered, they could revolutionize our understanding of physics by providing new insights into faster-than-light phenomena. They might offer solutions to questions about cosmic travel and communication that are currently constrained by relativity. Research into tachyons involves examining theoretical models and their implications for particle physics. Scientists explore how tachyons would fit within existing frameworks and what new physics might arise from their presence. The concept of tachyons has inspired various speculative theories and science fiction stories. These fictional accounts often explore the possibilities of faster-than-light travel and communication, driven by the notion of tachyons. Understanding tachyons requires investigating their interaction with the Higgs field and other fundamental forces. This could reveal whether they conform to or deviate from the established models of particle physics. Theoretical work on tachyons includes analyzing their role in quantum field theories. This research aims to determine if tachyons could exist within the quantum frameworks that describe the fundamental forces and particles of the universe. Despite the lack of empirical evidence, tachyons continue to be a topic of theoretical interest. They serve as a means to explore the limits of our current understanding and push the boundaries of known physics. Tachyons also pose questions about the energy and momentum of particles traveling faster than light. Their hypothetical properties would require a new understanding of these concepts, as they would not fit into the conventional equations of motion. The exploration of tachyons includes looking at their potential effects on information theory and communication. If they exist, they could offer ways to transmit information instantaneously, transforming our approaches to technology and data. In summary, tachyons are theoretical faster-than-light particles that challenge our current understanding of physics. While they have not been observed, their study stimulates discussion about the nature of spacetime and the limits of speed and causality. The Alcubierre drive is a theoretical concept proposed by physicist Miguel Alcubierre in 1994 that could potentially allow faster-than-light travel. The idea is based on manipulating spacetime to create a warp bubble that moves a spacecraft across vast distances. In this model, a spacecraft would be enclosed in a bubble of spacetime that contracts space in front of it and expands it behind. This would theoretically allow the spacecraft to travel faster than light, relative to the space outside the bubble, while the bubble itself moves at sublight speeds. The Alcubierre drive relies on the concept of negative energy density, which is necessary to stabilize and sustain the warp bubble. This exotic matter with negative energy would counteract the gravitational forces that would otherwise collapse the bubble. One of the key challenges with the Alcubierre drive is that we have yet to discover or produce the type of exotic matter needed. Without this matter, the theoretical model remains speculative and untested in practical terms. Theoretical calculations suggest that the energy requirements for an Alcubierre drive could be immense, potentially equivalent to the mass energy of entire planets or even stars. This makes the practical implementation of such a drive highly speculative with current technology. In the Alcubierre model, The spacecraft itself does not move within the bubble. Rather, the bubble moves through space, allowing the craft to reach distant locations quickly. This sidesteps the problem of traveling faster than light within the local frame of reference. The warp bubble created by the Alcubierre drive would need to be carefully shaped and controlled to avoid instability or collapse. Researchers are investigating ways to model and potentially mitigate these risks within theoretical frameworks. Recent developments in theoretical physics and cosmology continue to explore the feasibility of the Alcubierre drive. New insights into the nature of spacetime and exotic matter could impact the viability of this concept. One interesting aspect of the Alcubierre drive is its potential to transform our approach to space exploration. If feasible, it could enable interstellar missions that would otherwise take thousands of years with conventional propulsion methods. The idea of the Alcubierre drive has also inspired numerous science fiction stories which explore the possibilities of faster-than-light travel. These fictional accounts often dramatize the potential of warp drives to revolutionize space travel and exploration. Theoretical studies of the Alcubierre drive involve complex mathematics and models to address the potential issues of energy, stability, and exotic matter. These studies aim to refine the concept and understand its implications for physics and space travel. Exploring the Alcubierre drive also prompts discussions about the limits of current scientific knowledge and the potential for future breakthroughs. It encourages a deeper examination of fundamental physics and the nature of spacetime. In addition to its theoretical aspects, the Alcubierre drive raises philosophical questions about the future of space exploration and humanity's place in the cosmos. It challenges our imagination and inspires visions of a future where interstellar travel is possible. The concept of the Alcubierre drive underscores the need for innovative thinking in addressing the challenges of space travel. It highlights the importance of exploring unconventional ideas and pushing the boundaries of scientific understanding. As research into the Alcubierre drive progresses, it may provide new insights into the nature of spacetime and the possibilities for advanced propulsion technologies. This ongoing investigation contributes to our broader understanding of the universe. In summary, the Alcubierre drive presents a fascinating theoretical framework for faster-than-light travel by manipulating spacetime. While still speculative, it serves as a powerful concept for exploring the frontiers of physics and space exploration. Quantum entanglement is a phenomenon where two particles become interconnected in such a way that the state of one instantly influences the state of the other, regardless of distance. This interconnectedness seems to suggest that information could be exchanged faster than light. In entanglement, particles share a quantum state, meaning that changes to one particle's state are immediately reflected in the other. This appears to happen instantaneously, leading to speculation about whether it could enable faster-than-light communication. The concept of using entanglement for faster-than-light communication is known as quantum teleportation. This technique involves transmitting the quantum state of a particle to a distant location by entangling it with another particle and then measuring and reconstructing the state. However, despite the instantaneous nature of entanglement, quantum teleportation does not actually allow for faster-than-light communication. The process requires classical communication to complete, which is limited by the speed of light. Entanglement does not violate relativity because it does not transmit information in the traditional sense. The state changes are correlated, but do not convey usable data faster than light, thus preserving causality. Quantum entanglement challenges our understanding of information transfer and locality. It suggests that the quantum world operates differently from classical expectations, influencing how we think about space and time. Research into entanglement has practical applications in quantum computing and cryptography. These fields explore how entanglement can enhance computational power and secure communication, even if it doesn't enable faster-than-light travel. The limitations of quantum entanglement for faster-than-light communication have led to other theoretical ideas. Researchers continue to explore different quantum phenomena and their potential implications for advanced communication technologies. One alternative concept is the use of wormholes in conjunction with quantum entanglement. The idea suggests that entangled particles could be connected through a wormhole, potentially enabling instant communication across vast distances. Entanglement is also linked to the concept of quantum non-locality, where particles seem to act as if they are connected across space without direct interaction. This idea has profound implications for our understanding of the universe. Theoretical models exploring the combination of entanglement and wormholes face significant challenges. The practical realization of such ideas would require overcoming enormous technological and conceptual hurdles. While entanglement does not permit faster-than-light communication as currently understood, it remains a powerful tool for studying the fundamentals of quantum mechanics. Its exploration contributes to our deeper understanding of quantum phenomena. The study of entanglement also involves examining how it affects our concepts of reality and causality. It forces us to rethink how information and interactions are perceived in the quantum realm. Research into quantum entanglement and its applications is ongoing, with scientists striving to find new ways to harness these phenomena. Advances in quantum technology may provide new insights or applications that were previously considered impossible. The implications of entanglement extend beyond communication, influencing areas such as quantum mechanics, cosmology, and fundamental physics. These studies help shape our understanding of the universe at its most basic level. In summary, quantum entanglement presents intriguing possibilities for faster-than-light communication, but does not currently enable it due to the limitations of classical communication. It remains a key area of study in quantum physics, offering insights into the nature of reality and information. Causality violations occur when events are arranged in a sequence that contradicts the natural order of cause and effect. One well-known example is the grandfather paradox, which illustrates potential issues with traveling back in time. In the grandfather paradox, a time traveler goes back in time and prevents their own grandfather from meeting their grandmother. This act would mean the time traveler could never be born, raising questions about how they could have traveled back in time in the first place. The paradox highlights a fundamental problem with time travel. It creates a logical inconsistency where events negate themselves. This contradiction challenges our understanding of causality and the linear progression of time. And several theoretical solutions have been proposed to address such paradoxes, including the idea of parallel universes or alternate timelines. These solutions suggest that changes in the past might create a new, separate reality rather than affecting the original timeline. Another approach involves the many worlds interpretation, where every possible outcome of a time travel event creates a branching universe. In this view, time travel doesn't alter the original timeline, but instead spawns a new one where different outcomes unfold. Some theories propose that nature might have built-in mechanisms to prevent paradoxes. These mechanisms could ensure that certain events, like preventing one's own birth, are inherently impossible or self-correcting. The grandfather paradox is not just a theoretical curiosity but has practical implications for understanding fundamental physics. It challenges our grasp of how time and causality interact and how we might handle such paradoxes if time travel were possible. Exploring these paradoxes also leads to discussions about the limits of our current understanding of physics and the nature of time. They push the boundaries of how we conceptualize events and their sequences. The concept of causality violations extends beyond time travel to other areas of theoretical physics. It raises questions about how events are ordered and how changes in one part of a system can impact others. While these paradoxes are fascinating from a theoretical perspective, they remain speculative and not empirically proven. They serve as a tool for examining the consistency of our theories and models in physics. Philosophical implications of causality violations include questioning free will and determinism. If events can loop back and alter their own causes, it challenges the notion of a deterministic universe. Scientific investigations into causality and time travel often involve advanced mathematics and theoretical models. These studies aim to explore the implications of paradoxes and whether they can be reconciled with our understanding of physics. Addressing causality violations also involves considering the effects on fundamental physical laws. It requires rethinking how these laws operate across different contexts, including hypothetical scenarios involving time travel. Theoretical physicists continue to explore and debate the nature of causality and paradoxes. These discussions contribute to the broader quest for understanding the fundamental structure of reality and the potential for new physics. In speculative science fiction, causality paradoxes often serve as plot devices to explore complex themes. These stories offer imaginative ways to engage with the ideas of time travel and causality in ways that provoke thought and discussion. The study of causality violations and paradoxes remains an area of active research and debate. It challenges our understanding of the universe and invites ongoing exploration into the nature of time and reality. In summary, causality violations and the grandfather paradox illustrate the complex and intriguing problems associated with time travel. These concepts challenge our understanding of cause and effect and continue to inspire both scientific and philosophical inquiry. One of the major obstacles to faster-than-light travel is the immense energy required. According to current theories, reaching or exceeding the speed of light would require an infinite amount of energy, making such travel practically impossible. As an object's speed approaches the speed of light, its relativistic mass increases, meaning it effectively gains more mass as it accelerates. This increase in mass requires exponentially more energy to continue accelerating. The concept of infinite energy requirement arises from Einstein's theory of relativity, which implies that the closer an object gets to light speed, the more energy is needed to further increase its speed. This relationship creates a fundamental barrier to reaching or surpassing light speed. Even theoretical constructs like the Alcubierre drive, which suggest manipulating spacetime, face significant challenges with energy requirements. Estimates for such technologies involve energy scales far beyond anything humanity can currently produce. Theoretical models that propose faster-than-light travel often include energy requirements on the order of entire planets or even stars. These immense demands highlight the practical difficulties of achieving or sustaining such speeds. Efforts to overcome this challenge often involve exploring new physics or exotic matter. However, without discovering or creating feasible sources of such exotic matter, the energy problem remains a substantial hurdle. The energy requirements for faster-than-light travel also intersect with discussions on the feasibility of advanced propulsion technologies. Understanding and addressing these requirements is essential for any future developments in this field. Many of these theoretical models rely on speculative ideas about manipulating space-time or harnessing new types of energy. Until we have concrete discoveries, these remain intriguing but unproven concepts. Research into high-energy physics and cosmology continues to explore the limits of our understanding of energy and matter. These studies might provide insights into whether new physics could alter our approach to the energy requirements of faster-than-light travel. Current propulsion technologies, such as ion drives or nuclear propulsion, are vastly insufficient for achieving or approaching light speed. These methods provide a stark contrast to the theoretical demands of faster-than-light travel. Scientific inquiry into the infinite energy requirement explores whether there are alternative ways to approach or bypass this barrier. Innovations in energy generation and propulsion might offer new possibilities, though none are currently viable. The concept of infinite energy underscores the importance of practical limits in our scientific models. It challenges researchers to think creatively about how to reconcile theory with the practical realities of energy and technology. Addressing the energy problem involves interdisciplinary research, combining insights from physics, engineering, and cosmology. This collaborative approach aims to develop new theories or technologies that might eventually overcome these energy challenges. Advancements in energy generation or discovery of new physics could potentially reduce the energy requirements for high-speed travel. Until such breakthroughs occur, the infinite energy requirement remains a critical issue for faster-than-light exploration. In summary, the infinite energy requirement for faster-than-light travel represents a fundamental barrier in theoretical physics. Solving this problem would require revolutionary advances in both our understanding of energy and our technological capabilities. Hawking's chronology protection conjecture is a theoretical idea proposed by physicist Stephen Hawking to address potential time travel paradoxes. The conjecture suggests that the laws of physics might prevent the occurrence of time loops or paradoxical situations that could disrupt causality. According to Hawking, any attempts to create or utilize a time machine would be thwarted by natural mechanisms that prevent the formation of closed time-like curves. These curves would allow for time travel to the past, potentially leading to paradoxes like the grandfather paradox. Hawking's conjecture implies that even if theoretical models allow for time travel, the universe has built-in safeguards to prevent paradoxes from occurring. This concept aims to preserve the consistency of cause and effect in the face of time travel theories. The idea of chronology protection challenges the notion that time travel might be feasible under our current understanding of physics. It suggests that the universe has self-correcting mechanisms to prevent scenarios where causality could be violated. One proposed mechanism for chronology protection is the instability of hypothetical time machines. Hawking speculated that any attempt to create a time machine would lead to conditions that are dynamically unstable, preventing their operation. Hawking's conjecture also aligns with the broader principle of cosmic censorship, which posits that singularities or extreme distortions in spacetime are hidden from view. This principle serves to maintain the regularity of observable physics. The conjecture remains speculative but influential in discussions about the feasibility of time travel. It provides a framework for understanding why time travel might be inherently impossible or subject to natural constraints. While Hawking's conjecture does not definitively prove time travel is impossible, it presents a reasoned argument for why certain types of time travel could be prevented by physical laws. This idea is part of the ongoing debate within theoretical physics. Hawking's work on chronology protection also intersects with discussions about the fundamental structure of spacetime. It prompts questions about how time and causality are fundamentally linked and how they might be protected against anomalies. The conjecture has stimulated significant theoretical research, exploring ways to test or disprove the idea. Scientists investigate whether any empirical evidence or observations could support or challenge the notion of chronology protection. In the context of modern physics, Hawking's conjecture encourages a deeper examination of the possible limits of our theories about time and causality. It reflects an ongoing effort to reconcile the theoretical possibilities of time travel with observed physical laws. Hawking's conjecture has been influential in shaping discussions about the limits of time travel. It remains an important consideration in theoretical explorations of advanced physics and the nature of spacetime. The conjecture also highlights the need for a consistent framework that aligns with our observations of the universe. It represents an attempt to ensure that speculative theories do not lead to logical contradictions or violate fundamental principles. Exploring the implications of Hawking's conjecture involves examining how new discoveries in physics might affect our understanding of time travel. It serves as a guide for evaluating whether time travel is feasible within our current or future theoretical models. In summary, Hawking's chronology protection conjecture offers a theoretical perspective on preventing time travel paradoxes. It proposes that the laws of physics may inherently safeguard against such anomalies, preserving the consistency of causality and time. Negative energy and exotic matter are critical concepts in some theoretical models for faster-than-light travel, such as the Alcubierre drive. Negative energy is theorized to be necessary to stabilize a warp bubble and enable the manipulation of spacetime. However, negative energy remains a highly speculative idea with no empirical evidence to support its existence. The concept challenges our current understanding of energy and matter, which traditionally only includes positive energy. Exotic matter, a hypothetical form of matter with unusual properties like negative energy density, is also essential in these theories. Exotic matter would theoretically possess properties that counteract normal gravitational effects and could facilitate warp travel. One major issue with negative energy is that it contradicts known physical laws, such as the energy conditions in general relativity. These conditions generally prohibit the existence of negative energy densities in a stable form. Theoretical models suggest that negative energy might be derived from quantum fields or specific configurations of spacetime. However, the practical realization of such energy remains elusive and unverified by experiments. Exotic matter has been proposed in various forms, such as Casimir effect-based negative energy or speculative particles. Yet all these ideas face significant hurdles in terms of detection, creation, and manipulation. Creating and sustaining exotic matter would require technological advancements far beyond our current capabilities. This includes generating and maintaining conditions where negative energy can exist in a controlled manner. Additionally, the concept of exotic matter raises questions about stability and safety. The effects of introducing such matter into our universe are unknown and could potentially have unforeseen consequences. Research into negative energy and exotic matter often involves advanced theoretical physics and speculative scenarios. These investigations push the boundaries of our knowledge and explore possibilities that challenge established scientific frameworks. The lack of empirical evidence for negative energy or exotic matter means that these concepts remain purely theoretical. Scientists continue to explore their feasibility and implications, but have yet to confirm their existence or practical utility. Theoretical discussions about negative energy also intersect with broader issues in physics, such as the fundamental nature of energy and spacetime. These discussions help refine our understanding of these concepts and their role in advanced theoretical models. Efforts to detect or create exotic matter often involve high-energy physics experiments or sophisticated simulations. These experiments aim to probe the limits of our understanding and potentially uncover new forms of matter or energy. The speculative nature of negative energy and exotic matter highlights the need for ongoing research and critical examination. While these ideas offer exciting possibilities, they also underscore the importance of grounding theories in empirical evidence. The challenges associated with negative energy and exotic matter reflect the broader difficulties of advancing theoretical physics. They illustrate the complexities of reconciling theoretical models with observed physical realities. In summary, negative energy and exotic matter are central to some theoretical models of faster-than-light travel, but face significant challenges. Their speculative nature and lack of empirical evidence highlight the ongoing need for research and investigation in these areas. Faster-than-light travel presents numerous potential dangers that could have profound implications for both travelers and the universe. One major concern is the creation of high-energy impacts when traveling at or beyond light speed, which could result in catastrophic collisions with interstellar particles. Traveling at such extreme velocities might also generate immense gravitational forces, potentially affecting the structure of spacetime itself. These forces could pose risks to the stability of the spacecraft and to the fabric of spacetime around it. Another danger involves the potential for time paradoxes, such as those highlighted by the grandfather paradox. These paradoxes could disrupt causality and lead to unpredictable and potentially hazardous outcomes. The interaction between a superluminal spacecraft and normal matter could create significant energy release or radiation. This could have harmful effects on both the spacecraft and any nearby celestial objects or environments. There are also concerns about the accumulation of relativistic energy and its release upon deceleration. Abruptly stopping or slowing down could unleash destructive amounts of energy, posing a serious risk to the spacecraft and its surroundings. The potential for creating wormholes or other spacetime distortions introduces additional risks. These distortions could lead to unforeseen consequences, such as the destabilization of local spacetime or unintended alterations in the cosmic environment. Theoretical models suggest that faster-than-light travel might affect the entropy of the universe. Such alterations could have far-reaching effects on cosmic processes and the overall equilibrium of the universe. The safety of the crew and passengers is another critical consideration. The extreme conditions and unknown effects of FTL travel could pose significant risks to human health and the integrity of biological systems. The practical challenges of maintaining structural integrity at FTL speeds are immense. The forces involved could potentially damage or disintegrate spacecraft materials, leading to catastrophic failures. Exploring these dangers requires a thorough understanding of both theoretical and practical aspects of high-speed travel. Researchers must consider how to mitigate risks and ensure safety in the face of unknown variables. Technological advancements needed to achieve FTL travel also come with risks. Developing and managing new technologies could introduce unexpected hazards or complexities that must be carefully addressed. The potential for unintended interactions with other cosmic phenomena raises additional concerns. For example, altering the local spacetime could affect nearby stars, planets, or other celestial bodies in unforeseen ways. Theoretical safety measures might include advanced shielding or containment strategies to protect the spacecraft and its occupants. However, the effectiveness of such measures remains speculative and untested. The unknown nature of faster-than-light travel means that many of these dangers are theoretical and not yet fully understood. Ongoing research is essential to assess and address these potential risks. The impact of FTL travel on cosmic structures, such as galaxies or black holes, is another area of concern. Any large-scale disturbances could have significant and potentially dangerous consequences for the universe. In summary, while faster-than-light travel offers exciting possibilities, it also comes with numerous potential dangers. Understanding and mitigating these risks will be crucial for any future exploration of superluminal speeds. NASA has been exploring the concept of warp drives to potentially revolutionize space travel. Research in this area includes theoretical studies on how to manipulate spacetime to achieve faster-than-light travel. One notable project is the NASA Advanced Propulsion Physics Laboratory, often called the EagleWorks Laboratory. This lab focuses on theoretical concepts and experimental approaches related to advanced propulsion technologies, including warp drives. NASA's research into warp drives includes examining the Alcubierre drive, a theoretical model that proposes expanding and contracting space-time to create a warp bubble. The goal is to understand whether such concepts could be physically realizable or remain purely theoretical. The Alcubierre drive concept suggests that a spacecraft could achieve faster-than-light speeds by contracting space in front of it and expanding space behind it. NASA's research looks at the feasibility of generating and sustaining such a warp bubble. Challenges in NASA's research include understanding the energy requirements and the potential need for exotic matter. These components are essential for the theoretical models, but pose significant hurdles in terms of practical application. NASA has also investigated the theoretical implications of warp drives on spacetime and general relativity. This includes exploring how such technologies might interact with existing physical laws and whether they can be reconciled with our current understanding of the universe. The research includes both theoretical analysis and experimental efforts. This involves simulations and models to predict the behavior of warp drives and assess whether any practical experiments could validate these theories. Efforts to create a viable warp drive involve interdisciplinary collaboration, combining insights from physics, engineering, and computational sciences. Researchers aim to address the numerous technical and theoretical challenges involved. NASA's interest in warp drives aligns with its broader goals of advancing space exploration and technology. While warp drives remain speculative, their potential to transform space travel makes them a significant area of research. Theoretical studies also include examining potential breakthroughs in energy generation and material science that could make warp drives more feasible. NASA's research explores how advances in these fields might contribute to achieving faster-than-light travel. Challenges like the need for negative energy or exotic matter continue to be a focus of NASA's research. Understanding these requirements and exploring alternatives are crucial steps toward determining the viability of warp drives. NASA's research also considers the impact of warp drives on our understanding of physics. This includes evaluating whether such technologies would require new physical theories or modifications to existing ones. Publications and presentations from NASA researchers often detail their progress and findings. These contributions help to advance the scientific community's understanding of warp drives and their potential applications. NASA's research into warp drives is part of a broader exploration of advanced propulsion concepts. This includes studying other theoretical models and technologies that could revolutionize how we travel through space. The future of warp drive research depends on continued advancements in both theoretical and experimental physics. NASA remains at the forefront of investigating whether such technologies could eventually become reality. In summary, NASA's research into warp drives involves exploring the theoretical and practical aspects of faster-than-light travel. This includes addressing challenges, advancing related technologies, and evaluating the potential impact on our understanding of space and physics. Advances in quantum mechanics have introduced new ideas that could impact the feasibility of faster-than-light travel. Quantum entanglement and quantum field theories offer intriguing possibilities for understanding how particles might behave at or beyond light speed. One significant development is the study of quantum entanglement, where particles become interconnected in such a way that the state of one instantly affects the state of another, regardless of distance. This phenomenon raises questions about instantaneous information transfer and its implications for FTL communication. Quantum field theories, which describe how fields interact with particles, have also contributed to the discussion. These theories explore how manipulating quantum fields could potentially lead to new forms of faster-than-light travel or communication. Recent research into quantum mechanics has led to the exploration of concepts like quantum tunneling. This phenomenon allows particles to pass through barriers that would normally be insurmountable, suggesting possibilities for overcoming traditional limits of speed and distance. Quantum fluctuations, which are temporary changes in the energy of a point in space, might also offer insights into FTL travel. Understanding how these fluctuations interact with spacetime could provide clues about potential methods for achieving faster-than-light speeds. The concept of a quantum vacuum, where virtual particles constantly pop in and out of existence, might play a role in FTL theories. Researchers are investigating whether these quantum effects could be harnessed to manipulate spacetime in ways that support faster-than-light travel. Some theoretical models propose that harnessing quantum entanglement could lead to new methods of FTL communication. If entangled particles can transmit information instantaneously, it might offer a way to bypass traditional constraints of information transfer. Advances in quantum mechanics also involve exploring the nature of spacetime at the quantum level. Understanding how spacetime behaves at extremely small scales could reveal new possibilities for manipulating it in ways that might support FTL travel. The integration of quantum mechanics with general relativity is a key area of research. Finding a unified theory that reconciles these two domains might offer new insights into the nature of spacetime and the feasibility of faster-than-light travel. Recent experiments in quantum mechanics, such as those involving high-energy particles or advanced quantum systems, are helping to test these ideas. These experiments provide valuable data that could inform our understanding of FTL possibilities and limitations. Theoretical advancements in quantum mechanics continue to push the boundaries of what we know about the universe. These developments offer potential pathways for overcoming the challenges of faster-than-light travel and expanding our understanding of physical laws. Researchers are also investigating how quantum mechanics could impact the concept of spacetime itself. Innovations in this field could lead to new theories or technologies that might make FTL travel more feasible. The role of quantum mechanics in FTL travel includes examining how quantum effects could be utilized or overcome. This research is crucial for understanding whether new technologies might arise from our evolving knowledge of quantum phenomena. Exploring the intersection of quantum mechanics and faster-than-light travel involves considering both theoretical models and practical experiments. These efforts aim to bridge the gap between current scientific understanding and future technological possibilities. Advances in quantum mechanics may also lead to novel approaches for energy manipulation, which could impact FTL travel. Discovering new methods for controlling energy at the quantum level might help address some of the challenges associated with faster-than-light speeds. In summary, advances in quantum mechanics offer promising avenues for exploring the possibilities of faster-than-light travel. These developments provide new insights into quantum phenomena and their potential implications for space exploration and technology. Simulations of wormholes offer valuable insights into their theoretical stability and practical feasibility. Researchers use complex models to analyze how wormholes might behave under various conditions and what factors could influence their stability. One key focus of these simulations is understanding the conditions required to keep a wormhole open. This involves exploring the effects of different types of exotic matter or energy that might be needed to counteract gravitational forces. Simulations also examine the potential risks associated with wormholes, such as their tendency to collapse. By modeling different scenarios, scientists aim to determine how stable wormholes might be and whether they could safely support travel or communication. Advanced computational techniques are employed to simulate the behavior of wormholes in dynamic environments. These techniques help researchers predict how wormholes might interact with other cosmic phenomena and whether they could remain stable over time. Researchers also simulate the effects of perturbations on wormholes, such as changes in energy density or external forces. Understanding how these perturbations affect stability is crucial for assessing the practicality of using wormholes for space travel. Simulations often involve creating detailed models of wormhole structures, including their geometry and the distribution of energy. These models help scientists visualize how wormholes might function and how different factors could impact their stability. One aspect of these simulations is testing theoretical limits and boundaries. Researchers explore the extreme conditions under which wormholes might remain stable and identify scenarios where they could become unstable or collapse. The results from wormhole simulations provide insights into the feasibility of creating and maintaining such structures. By analyzing these results, scientists can better understand the challenges and potential solutions for practical applications. Simulating wormholes also involves examining the potential for unintended consequences, such as the creation of singularities or other anomalies. These unintended effects must be accounted for to ensure that wormholes do not pose significant risks. Researchers use a combination of theoretical physics and computational modeling to study wormholes. This interdisciplinary approach helps bridge the gap between abstract theories and practical simulations, providing a more comprehensive understanding. Simulations of wormholes are often tested against known physical laws and principles. This helps validate whether the models are consistent with our understanding of gravity, spacetime, and quantum mechanics. The stability of wormholes in simulations is assessed by evaluating various factors, such as energy requirements and structural integrity. These assessments help determine whether wormholes could be viable for practical use, or if they remain purely theoretical. Researchers also investigate how wormholes might interact with matter and energy in their vicinity. Understanding these interactions is crucial for assessing the safety and functionality of wormholes in real-world scenarios. Simulations continue to evolve as computational power increases and our understanding of physics deepens. Advances in these areas contribute to more accurate models and a better understanding of wormhole stability. The data from wormhole simulations inform ongoing theoretical research and experimental efforts. This feedback loop helps refine our theories and approaches, moving us closer to understanding whether wormholes could be feasible. In summary, simulations of wormholes play a critical role in exploring their stability and potential applications. These simulations provide insights into the theoretical and practical aspects of wormholes, contributing to our understanding of their feasibility. The Large Hadron Collider, or LHC, is one of the most powerful tools used in the search for tachyons. As the world's largest and most powerful particle accelerator, the LHC explores fundamental particles and forces, testing theories that include the existence of tachyons. Researchers at the LHC investigate tachyons by looking for evidence of particles that travel faster than light. They use high-energy collisions to create conditions that might reveal these elusive particles if they exist. Tachyons are theoretical particles that, according to some theories, move faster than the speed of light. The LHC's experiments aim to detect any anomalies or signals that could suggest the presence of such particles. The LHC's experiments involve smashing protons and other particles together at incredibly high energies. By analyzing the results of these collisions, scientists search for signs that could indicate the presence of tachyons. Detecting tachyons would involve identifying unexpected patterns or results in the data from these high-energy collisions. The LHC's advanced detectors and data analysis systems are designed to capture and scrutinize these potential signals. One approach in tachyon hunting is to look for indirect evidence. This includes searching for effects that tachyons might have on other particles, or on the overall dynamics of the collision events. Theoretical models suggest that tachyons could produce specific signatures in particle collisions. Researchers use these predictions to guide their search and refine their experiments. Despite extensive research, no direct evidence of tachyons has been observed at the LHC so far. However, the search continues, as finding such particles would have profound implications for our understanding of physics. The LHC's capabilities allow for high-precision measurements and the exploration of new theoretical possibilities. This makes it a crucial instrument in the ongoing quest to uncover the mysteries of tachyons. Researchers also consider the impact of tachyons on existing theories and models. Discovering tachyons would require revising our understanding of particle physics and faster-than-light travel. The search for tachyons is part of a broader effort to explore the fundamental nature of the universe. The LHC plays a key role in testing theories that challenge our current understanding of physics. Advanced computational tools and simulations are used to predict how tachyons might behave. These predictions help guide the design of experiments and the interpretation of data from the LHC. The LHC's experiments are designed to explore a wide range of possibilities, including the potential existence of tachyons. This involves testing various theoretical models and searching for anomalies in experimental results. Although finding tachyons would be a groundbreaking discovery, the search is challenging due to the lack of clear theoretical signatures. Researchers must be meticulous in their analysis to distinguish potential tachyon signals from background noise. The LHC's research into tachyons also contributes to our understanding of fundamental physics. Even in the absence of direct evidence, the experiments provide valuable insights and refine our knowledge of high-energy particle interactions. The ongoing efforts at the LHC reflect the importance of exploring new and unconventional theories. The search for tachyons highlights the dynamic nature of scientific inquiry and the quest to understand the universe's deepest mysteries. Leading scientists have proposed various theories and models to explore the possibility of faster-than-light travel. These theories range from speculative ideas to serious scientific investigations into the limits of our current understanding. One prominent scientist, Kip Thorne, has contributed significantly to the study of wormholes and their potential for faster-than-light travel. His work on the theoretical feasibility of wormholes and their stability provides a foundation for further research in this area. Michio Kaku, a well-known theoretical physicist, has also explored the concept of warp drives and their implications. His discussions on the possibilities of manipulating spacetime align with ongoing efforts to understand how FTL travel might be achieved. Another influential figure, Harold White, leads NASA's Advanced Propulsion Physics Laboratory and has been involved in studying warp drive concepts. His research focuses on the theoretical underpinnings of warp drives and their potential to revolutionize space travel. Theoretical physicist Eric Lentz has investigated the practical aspects of creating and sustaining wormholes. His work includes detailed analyses of the energy requirements and stability conditions necessary for wormholes to function. Roger Penrose, renowned for his contributions to general relativity and cosmology, has examined the implications of faster-than-light travel on our understanding of spacetime. His theories challenge conventional views and inspire new approaches to exploring FTL possibilities. Sean Carroll, a prominent cosmologist, has addressed the theoretical limits of FTL travel in the context of quantum mechanics and general relativity. His research examines how these fundamental theories might be reconciled with the idea of faster-than-light travel. James Gates, known for his work in supersymmetry and string theory, has explored how advanced theoretical frameworks could support FTL concepts. His research includes investigating whether string theory offers any pathways to achieving faster-than-light speeds. Gordon Kane has examined the connections between high-energy physics and theoretical models of FTL travel. His work contributes to understanding how fundamental particles and forces might interact with concepts like warp drives and wormholes. Theoretical physicist Juan Maldacena has studied the implications of FTL travel in the context of holographic principles and black hole physics. His research explores whether these advanced theories offer any insights into achieving faster-than-light travel. Other scientists, such as Alan Guth, have investigated the role of inflationary theory in understanding the early universe. His work provides a broader context for exploring how rapid expansion might relate to concepts of faster-than-light travel. Roger Penrose's work on cosmic censorship and singularities also impacts discussions about FTL travel. His theories on the structure of spacetime and its limits contribute to the broader debate on whether FTL travel could be feasible. Scientists like Lisa Randall have explored higher dimensions and their potential role in understanding the constraints of FTL travel. Her research into extra dimensions offers alternative perspectives on how space-time might be manipulated. Stephen Hawking's theories on black holes and the nature of the universe provide insights into the extreme conditions under which FTL concepts might be tested. His work continues to influence discussions about the fundamental limits of speed and travel. David Deutsch has contributed to the understanding of quantum mechanics and its implications for FTL travel. His research includes examining how quantum theories might interact with concepts like wormholes and tachyons. Overall, leading scientists from various fields contribute to the ongoing exploration of faster-than-light travel. Their diverse theories and models help shape our understanding and push the boundaries of what might be possible in the realm of high-speed travel. The concept that faster-than-light travel might be impossible is often linked to fundamental principles like the conservation of energy. According to this principle, energy cannot be created or destroyed, only transformed, which poses challenges for theories proposing FTL travel. In the context of FTL travel, conservation of energy implies that achieving such speeds would require enormous amounts of energy. This energy requirement grows exponentially as objects approach the speed of light, making FTL travel seem impractical. Relativistic physics suggests that as an object accelerates, its mass effectively increases, requiring more and more energy to continue accelerating. Reaching or exceeding the speed of light would require infinite energy, a concept that conflicts with the conservation of energy. The conservation of momentum also plays a role in this discussion. As objects move faster, their momentum increases, which further complicates the possibility of reaching or exceeding light speed without violating fundamental physical laws. Theoretical models often propose exotic forms of energy or matter to overcome these constraints, such as negative energy or dark energy. However, these concepts are speculative and face their own set of challenges and uncertainties. Another consideration is the requirement for energy to stabilize structures like wormholes or warp drives. The amount of energy needed to maintain these structures under FTL conditions raises significant questions about feasibility and aligns with conservation principles. The idea of harnessing energy from alternative sources like vacuum fluctuations has been explored. However, the practicality of such methods in the context of FTL travel remains highly speculative and challenging to implement. Energy conservation laws also imply that creating or sustaining a warp bubble for faster-than-light travel would demand a colossal amount of energy. This demand poses significant practical obstacles given our current technological capabilities. Simulations and theoretical models often highlight the gap between theoretical FTL concepts and practical energy requirements. These models must address how to manage or mitigate energy constraints in any feasible FTL scenario. The conservation of energy principle also impacts the search for exotic matter or negative energy. While these ideas offer potential solutions, they are still theoretical and have not been observed or experimentally verified. Incorporating conservation laws into FTL theories involves rigorous analysis of how energy and momentum would be balanced. This analysis helps determine whether proposed FTL mechanisms are consistent with known physical principles. Some theories suggest that if FTL travel were possible, it might involve new forms of energy or physics beyond our current understanding. However, integrating such theories with conservation laws remains a significant challenge. The debate over FTL travel often centers around whether the energy requirements and principles of conservation can be reconciled with theoretical models. This debate drives ongoing research and exploration into the limits of physics. Alternative approaches, like exploring quantum effects or higher dimensional theories, aim to address energy conservation challenges. These approaches seek to provide new insights into how FTL travel might be achieved without violating fundamental laws. The conservation of energy remains a cornerstone of modern physics, influencing how we understand and approach FTL travel. Addressing this principle in theoretical models is crucial for evaluating the viability of faster-than-light concepts. As research progresses, scientists continue to test the limits of energy conservation and its implications for FTL travel. This ongoing exploration is essential for refining our understanding and developing feasible theories. Some physicists dismiss faster-than-light travel as fantasy due to the fundamental constraints of known physics. The overwhelming consensus is that FTL travel violates established theories such as Einstein's theory of relativity, which has been rigorously tested and confirmed. The massive energy requirements associated with FTL travel are another reason for skepticism. The energy needed to accelerate an object to or beyond the speed of light would be astronomical, far beyond our current technological capabilities. Many scientists argue that the theoretical constructs needed for FTL travel, like warp drives or wormholes, rely on hypothetical forms of matter and energy that have not been observed. The lack of empirical evidence for these exotic components raises doubts about their feasibility. The potential for causality violations, such as time travel paradoxes, also contributes to the dismissal of FTL travel. These paradoxes challenge our understanding of time and causality, raising concerns about the consistency of such theories. Some physicists believe that the mathematical models used to propose FTL travel are speculative and lack physical grounding. Theoretical constructs that involve altering spacetime in ways not yet observed face significant scrutiny from the scientific community. The principles of relativity suggest that as objects approach the speed of light, their mass increases, requiring exponentially more energy. This intrinsic limitation leads many to conclude that surpassing light speed is inherently impossible. Concerns about the stability and practicality of hypothetical constructs, like wormholes or warp drives, further fuel skepticism. Even if such constructs were theoretically possible, their practical implementation presents significant and unresolved challenges. The absence of any experimental confirmation of tachyons or other faster-than-light particles reinforces the skepticism. Without direct evidence, many physicists remain unconvinced that FTL travel is anything more than theoretical speculation. Scientific consensus often reflects a conservative approach to extraordinary claims. Until there is compelling evidence or a breakthrough in understanding, many physicists view FTL travel as an intriguing but unlikely possibility. Theoretical discussions about FTL travel often encounter issues with reconciling them with established physical laws. The need for new physics or a major revision of current theories to accommodate FTL travel is seen as a significant barrier. Debates about FTL travel also highlight the difference between speculative theories and practical science. Many scientists focus on more immediate and empirically supported avenues of research, considering FTL travel a less productive area of inquiry. The challenges associated with energy conservation and mass increase further compound the doubts about FTL travel. These challenges are not easily addressed by current scientific models, reinforcing the view that FTL is improbable. Some physicists argue that the pursuit of FTL travel diverts attention from more plausible scientific advancements. They advocate for focusing on research areas that align more closely with current scientific knowledge and technological progress. Theoretical models proposing FTL travel often require complex and unproven concepts. The reliance on speculative ideas without solid experimental support leads many to question the validity of such theories. Skepticism about FTL travel also arises from the historical track record of speculative scientific ideas. Many concepts once considered implausible have been disproven or revised, influencing how scientists approach new, speculative theories. The concept that the universe acts as a light-speed limit enforcer stems from the idea that the speed of light is a fundamental constraint imposed by the structure of spacetime. This viewpoint suggests that the universe is inherently designed to prevent any object from exceeding this cosmic speed limit. According to this concept, the fabric of spacetime itself is shaped by the speed of light, which serves as a universal speed limit. The properties of spacetime ensure that no information or matter can travel faster than this limit, maintaining the consistency of physical laws. Some theories propose that any attempt to surpass the speed of light would encounter immense resistance from spacetime. This resistance would act as a natural barrier, making faster-than-light travel practically impossible within the current framework of physics. The idea also suggests that the speed of light is a fundamental constant that stabilizes the structure of the universe. By enforcing this limit, the universe preserves the balance of physical forces and the coherence of causality across space and time. Theoretical models often argue that exceeding light speed would lead to contradictions in our understanding of physics. These contradictions include issues with causality, time travel, and the fundamental principles that govern the behavior of matter and energy. The concept of spacetime as a light-speed limit enforcer implies that any hypothetical FTL mechanisms would require altering the very fabric of spacetime. Such alterations would need to address how the universe enforces this speed limit while allowing for new forms of travel. In this framework, the universe's light speed limit ensures that fundamental laws, such as the conservation of energy and momentum, remain intact. This constraint helps maintain the stability of physical interactions and the overall structure of the cosmos. The notion that the universe enforces this speed limit aligns with the principle of causality, which dictates that cause must precede effect. By restricting speeds to below light speed, the universe preserves this temporal order and prevents paradoxes. Scientific models that incorporate the speed of light as a limit often emphasize the uniformity of physical laws. This uniformity ensures that no region of space or time can violate the speed of light constraint, reinforcing the idea of a universal speed limit. The concept also intersects with the idea that the speed of light is related to the maximum rate at which information can be transmitted. This connection underlines the role of the speed limit in maintaining the coherence of information across the universe. Some theories suggest that any attempt to bypass the light speed limit would require new exotic forms of matter or energy. These forms would need to circumvent the constraints imposed by spacetime while aligning with known physical principles. The enforcement of the light speed limit by the universe may also be linked to the structure of space and time itself. By constraining speeds to below light speed, the universe ensures that all interactions remain consistent and predictable. In this context, any proposed methods for achieving faster-than-light travel must address how they would interact with or alter the universe's natural constraints. This challenge highlights the difficulty of reconciling such methods with established physical laws. The concept of the universe as a light-speed limit enforcer underscores the fundamental nature of the speed of light in our understanding of physics. It serves as a boundary that defines the limits of what is currently considered physically possible. The theoretical exploration of FTL travel often involves questioning the rigidity of this speed limit. However, any successful theory would need to account for how it modifies or interacts with the universe's inherent constraints on speed. Overall, the idea that the universe enforces a light speed limit provides a framework for understanding why FTL travel remains speculative. This concept integrates with broader principles of physics that govern the behavior of matter, energy, and space-time. Potential flaws in faster-than-light theoretical models often stem from their reliance on unproven assumptions. These models frequently depend on exotic matter or energy that has not been experimentally observed, making their practical feasibility questionable. Many FTL theories require conditions or components that challenge our understanding of fundamental physics. For instance, the need for negative energy to stabilize a warp drive remains speculative and lacks empirical support. Another issue is the mathematical complexity of FTL models, which can lead to predictions that may not align with physical reality. Theoretical models often involve complex equations that may not fully capture the behavior of spacetime under such extreme conditions. Some FTL concepts, like wormholes or warp drives, rely on manipulating spacetime in ways that could lead to paradoxes or contradictions. These paradoxes raise concerns about the internal consistency of such theories and their alignment with known physical laws. The energy requirements for FTL travel, as predicted by current models, are often beyond our technological capabilities. Theoretical projections suggest that achieving or surpassing light speed would necessitate more energy than is practical or feasible with today's technology. FTL models sometimes assume idealized conditions that may not be achievable in the real universe. These assumptions can lead to predictions that do not account for practical limitations or the true nature of spacetime. Some theories propose that FTL travel would require altering the structure of spacetime itself, which introduces significant uncertainty. The impact of such alterations on the overall stability of the universe is not well understood. The potential for causality violations and time travel paradoxes poses a significant challenge to FTL theories. Any model that allows for faster-than-light travel must address how it reconciles these issues without creating logical inconsistencies. Theoretical models often use approximations that may not accurately reflect the complexities of spacetime at FTL speeds. These approximations can lead to flawed predictions or misunderstandings about the feasibility of such travel. The speculative nature of many FTL theories means they are built on foundations that are not yet confirmed by experimental evidence. This lack of empirical verification undermines the reliability of these models. Certain FTL concepts involve scenarios where fundamental physical constants, like the speed of light, might be altered. Such changes challenge our current understanding of these constants and their role in maintaining the consistency of physical laws. Many FTL models require exotic forms of matter that would have unusual properties, such as negative mass. Theoretical discussions about these properties are often speculative and lack observational support. Some proposed FTL mechanisms suggest that enormous amounts of energy could be stored or manipulated in ways that defy current physical theories. The practicality of such mechanisms remains highly questionable. Theoretical models must also consider how FTL travel would impact local and global physics. The interaction between proposed FTL methods and established physical laws is a significant area of concern. The complexity and speculative nature of FTL theories can make them difficult to test or validate. This challenge means that many models remain purely theoretical and have not undergone rigorous experimental scrutiny. Finally, the integration of FTL concepts with known physical laws often reveals gaps or inconsistencies. These gaps highlight the need for further research and refinement to address potential flaws in the theoretical framework. Faster-than-light travel challenges our understanding of physics by directly contradicting established principles such as Einstein's theory of relativity. According to relativity, as objects approach the speed of light, their mass increases and requires more energy, making FTL travel seemingly impossible. One major challenge is the concept of causality, which is central to our current understanding of time and space. FTL travel could lead to scenarios where effects precede their causes, creating paradoxes that challenge the fundamental order of events in the universe. Additionally, FTL travel implies the need for exotic forms of matter or energy that have not been observed. This introduces elements into our physical theories that are not only unverified, but may also require revisions to our understanding of fundamental forces. The energy requirements for FTL travel, as proposed by various theories, are often astronomical. These requirements suggest that surpassing the speed of light would involve manipulating energy in ways that defy our current technological capabilities and understanding. The integration of FTL concepts often involves theoretical constructs that disrupt the consistency of spacetime. For example, models involving wormholes or warp drives suggest altering spacetime geometry, which could have unforeseen consequences on the stability of the universe. FTL theories also raise questions about the conservation of energy and momentum, which are fundamental to classical mechanics. Any proposed method for achieving FTL speeds must address how these conservation laws are maintained or altered in such scenarios. The speculative nature of FTL travel also introduces new and complex variables into our physics models. These variables, such as negative energy or hypothetical particles, challenge the robustness of current scientific theories and require substantial theoretical adjustments. Causality violations introduced by FTL travel could undermine our understanding of the causal relationship between events. This would require a rethinking of how time and space interact, potentially leading to a fundamental overhaul of physical laws. Theoretical models of FTL travel often rely on complex mathematics that may not fully capture the real-world implications. These models can sometimes lead to predictions that do not align with observable phenomena, highlighting potential gaps in our current theories. Proposing mechanisms for FTL travel often involves adjusting or bypassing established physical constants, such as the speed of light. This raises questions about the nature of these constants and their role in maintaining the coherence of physical laws. The potential paradoxes and contradictions introduced by FTL travel can create significant challenges for theoretical physics. Resolving these issues requires a deep understanding of how such travel interacts with the principles of relativity and quantum mechanics. FTL travel also brings up issues related to the nature of spacetime itself. Any theory that allows for speeds exceeding light must reconcile how such speeds impact our understanding of spacetime continuity and structure. Theoretical physics often relies on well-established principles to build new models. Introducing FTL concepts disrupts this foundation, requiring physicists to explore new frameworks that might alter our basic understanding of the universe. The feasibility of FTL travel necessitates revisiting fundamental questions about the limits of physical laws. This process involves reassessing what we know about energy, mass, and the fundamental nature of spacetime. Finally, the challenge of integrating FTL travel into our existing physical theories underscores the need for innovative thinking. It calls for novel approaches to understanding how such travel could be possible within the constraints of known physics. In science fiction, faster-than-light travel is a popular concept that captures the imagination of audiences. Iconic examples often showcase advanced technologies that allow characters to traverse vast distances in the blink of an eye. One classic example is the warp drive from the Star Trek franchise. This technology enables starships to travel faster than light by warping space around them, allowing for quick interstellar journeys. Another well-known depiction is the hyperdrive from the Star Wars universe. Hyperdrive allows spacecraft to jump to light speed, bypassing normal space and making intergalactic travel feasible. In the novel The Hitchhiker's Guide to the Galaxy, the infinite improbability drive is a humorous take on FTL travel. It allows a spaceship to reach any point in the universe almost instantaneously by manipulating improbability. Arthur C. Clarke's Rendezvous with Rama features a concept of FTL travel through the use of a mysterious alien spacecraft. This vehicle hints at advanced technologies that push the boundaries of human understanding. In Ender's Game by Orson Scott Card, the Ansible is a device that allows for instantaneous communication across light years. Though not a method of travel, it represents the potential for FTL communication in science fiction. The jump drive from the Honor Harrington series by David Weber enables ships to travel across vast distances almost instantaneously. This technology is integral to the series' depiction of space warfare and exploration. The Tesseract, in Madeleine L'Engle's A Wrinkle in Time, provides a different take on FTL travel. Characters travel through a higher dimensional space, allowing them to traverse vast distances quickly. In The Martian by Andy Weir, while the focus is on near-future technology, FTL travel is hinted at as a possibility for future exploration. This speculative idea reflects ongoing interest in overcoming the limits of current space travel. The slipstream technology in the Stargate series allows for near-instantaneous travel between distant points in the galaxy. This concept is central to the show's premise of interstellar exploration. In Isaac Asimov's Foundation series, the concept of hyperspace is used for FTL travel. Spaceships enter this alternate dimension to travel faster than light and reach distant stars. The faster-than-light drive in the Mass Effect video game series enables travel between star systems in a matter of minutes. This technology is a key element of the game's expansive universe. In Doctor Who, the TARDIS utilizes a form of FTL travel to move through time and space. The TARDIS's ability to traverse any point in the universe instantly is a central aspect of the show. The Alcubierre drive mentioned in the Expanse series, inspired by real scientific theories, provides a speculative but grounded take on FTL travel. It involves creating a bubble of space that moves faster than light. In 2001, A Space Odyssey, while not directly addressing FTL, the concept of advanced technology hints at future possibilities. The monoliths suggest that humanity may eventually overcome current limitations. In The Three-Body Problem by Liu Cixin, the concept of light-speed barriers is explored, reflecting on the limitations and possibilities of FTL travel in a complex universe. The Stargate franchise also features the Gate network, allowing for near-instantaneous travel between different planets. This network serves as a practical method for exploring distant worlds in the series. Science fiction often serves as a source of inspiration for real scientific advancements. The imaginative concepts explored in fiction can spark curiosity and drive researchers to explore previously uncharted territories. Many scientific breakthroughs have been influenced by ideas first introduced in science fiction. For example, the concept of personal communicators in Star Trek foreshadowed the development of modern mobile phones. The portrayal of space travel in science fiction can also inspire advancements in aerospace engineering. The vision of interstellar travel often encourages scientists and engineers to push the boundaries of current space exploration technologies. Science fiction speculative technologies often provide a framework for scientists to develop real-world applications. Concepts like artificial intelligence and robotics, explored in fiction, have led to significant progress in these fields. Fictional depictions of advanced medical technologies can lead to real-world research into similar innovations. For instance, the idea of diagnostic devices from shows like Star Trek has influenced the development of modern medical imaging techniques. The portrayal of futuristic energy sources in science fiction can motivate researchers to explore alternative energy solutions. Ideas about efficient power sources often lead to experimental work in renewable and advanced energy technologies. Science fiction can also play a role in shaping public perception of scientific research. By depicting futuristic technologies, it helps society envision what might be possible and fosters support for scientific endeavors. The exploration of ethical dilemmas in science fiction often parallels real-world scientific debates. These fictional scenarios provide a platform for discussing the moral implications of new technologies and their potential impact on society. Science fiction can inspire collaborative efforts between scientists and engineers. By presenting novel ideas and scenarios, it encourages interdisciplinary work that can lead to groundbreaking innovations. The imaginative solutions presented in science fiction often challenge scientists to think outside the box. This creative thinking can lead to new approaches and solutions in real-world scientific research. Many technological innovations have been driven by ideas that originated in science fiction literature. The creative visions of future technologies often provide a blueprint for engineers and inventors to develop practical applications. The concept of space exploration and colonization in science fiction can drive advancements in space technology. It motivates scientists to develop new propulsion systems and life support technologies for future missions. Science fiction often introduces futuristic concepts that become real-world goals. The portrayal of space habitats and advanced robotics has inspired actual research into building sustainable environments and autonomous machines. The speculative nature of science fiction allows for the exploration of theoretical ideas that may become practical in the future. This speculative thinking can lead to new scientific hypotheses and experimental approaches. Science fiction's portrayal of advanced computing and virtual realities can influence developments in these areas. The vision of immersive digital environments often leads to advancements in virtual reality and artificial intelligence technologies. Finally, science fiction helps to fuel the imagination of young scientists and engineers. By presenting exciting possibilities, it encourages the next generation to pursue careers in science and technology. The concept of faster-than-light travel has left a significant mark on popular culture, shaping how we envision the future. From movies to literature, FTL travel often represents humanity's quest for exploration and adventure. In cinema, faster-than-light travel is a staple of the science fiction genre, often depicted with dazzling visuals and imaginative technologies. Films like Star Wars and Star Trek have introduced audiences to a universe where space travel is limited only by the bounds of imagination. Literature has also embraced FTL travel as a central theme, exploring the possibilities of interstellar journeys and their impact on civilization. Authors such as Isaac Asimov and Arthur C. Clarke have crafted narratives that delve into the implications of breaking light-speed barriers. The idea of FTL travel has inspired countless fan theories and speculative fiction, reflecting a collective fascination with the concept. Enthusiasts often engage in discussions about how such technologies could be developed or what they might mean for the future. FTL travel concepts also influence the design of futuristic technologies in real-world applications. Engineers and designers often draw on sci-fi portrayals to envision new technologies and their potential benefits. The portrayal of FTL travel in media often serves as a metaphor for human ambition and the drive to overcome limitations. It represents our desire to explore the unknown and push beyond the constraints of current technology. The idea of instantaneously traversing vast distances has become a symbol of hope for future space exploration. It fuels the imagination of those who dream of reaching distant stars and discovering new worlds. In gaming, FTL travel is frequently used as a gameplay mechanic, allowing players to experience space exploration and interstellar conflict. Games like Elite Dangerous and No Man's Sky allow players to explore procedurally generated universes, embodying the dream of limitless space travel. The fascination with FTL travel has led to a cultural phenomenon where it is often featured in discussions about the future of humanity. It represents both the excitement and challenges of venturing into the cosmos. FTL travel has also influenced the development of new media and entertainment formats. Virtual reality experiences and interactive storytelling often incorporate concepts of advanced space travel to engage audiences. The concept continues to inspire scientific curiosity and technological innovation. As researchers and engineers consider the possibilities of FTL travel, they often reference its depiction in science fiction as a source of inspiration and aspiration. Cultural representations of FTL travel often reflect our broader hopes and anxieties about technological advancement. They can highlight the potential benefits and risks associated with pushing the boundaries of human knowledge. FTL travel in fiction frequently explores themes of human perseverance and the quest for knowledge. It underscores our collective imagination and the drive to understand our place in the universe. The impact of FTL concepts extends to art and design, influencing visual representations of space and technology. Artists often use these ideas to create stunning depictions of futuristic worlds and advanced spacecraft. FTL travel has become an enduring symbol in popular culture, representing the ultimate frontier of exploration. Its portrayal in various media continues to capture the imagination and inspire new generations to dream big about the future. Finally, the cultural impact of FTL travel concepts reveals our deep-seated desire to break free from the constraints of our current reality. It embodies the spirit of discovery and the pursuit of the unknown that drives both science and storytelling. In science fiction, faster-than-light travel is often portrayed with varying degrees of realism and fantasy. Realistic portrayals attempt to ground FTL concepts in plausible scientific principles, while fantastical depictions push the boundaries of imagination. Some sci-fi works strive for scientific accuracy, presenting FTL travel within the constraints of known physics. These portrayals might use speculative theories like warp drives or wormholes to explore how such technologies could theoretically function. In contrast, fantastical portrayals of FTL travel often prioritize dramatic effect over scientific plausibility. Films and books in this category might depict instantaneous travel or warp speeds that defy our current understanding of physics. Realistic portrayals might focus on the challenges and limitations of FTL travel, such as energy requirements and time dilation. They often explore the technical and ethical implications of breaking the light speed barrier. Fantastical depictions, on the other hand, often simplify or ignore these complexities to create exciting narratives. They might feature sleek spacecraft that travel across galaxies in mere moments, focusing on adventure and spectacle. The portrayal of FTL in realistic sci-fi often reflects contemporary scientific debates and research. It might incorporate emerging theories and technological concepts, presenting a vision of the future grounded in current knowledge. Fantastical portrayals might create entirely new physics or technology, embracing the creative freedom of speculative fiction. These depictions often serve as a canvas for exploring philosophical and existential themes. Realistic FTL travel concepts can also influence real-world scientific research. By presenting scientifically plausible ideas, they inspire researchers to investigate the feasibility of advanced technologies. Fantastical portrayals, while less scientifically grounded, can captivate audiences with their imaginative worlds and epic journeys. They offer a form of escapism and adventure that stretches the limits of what we believe is possible. The distinction between realistic and fantastical FTL travel highlights the tension between science and imagination. Realistic portrayals aim to remain within the bounds of known science, while fantastical ones explore what could be possible if those bounds were stretched. Realistic sci-fi often includes detailed explanations and technical jargon to lend credibility to its FTL concepts. This approach appeals to audiences interested in science and technology, offering a more grounded exploration of advanced travel. Fantastical portrayals tend to focus on the emotional and narrative aspects of FTL travel. They emphasize the wonder and excitement of exploring new worlds, often at the expense of scientific accuracy. Both realistic and fantastical portrayals contribute to the broader cultural understanding of FTL travel. They shape how people envision the future and influence the aspirations of scientists and engineers. The blend of realistic and fantastical elements in some sci-fi works can provide a balance between scientific feasibility and imaginative storytelling. This approach allows for creative exploration while acknowledging the limitations of current science. Realistic portrayals might use FTL travel as a backdrop for exploring complex scientific and philosophical issues. They often integrate detailed world-building and character development to enhance the narrative. Fantastical portrayals of FTL travel can serve as a metaphor for human ambition and exploration. They offer a way to examine our desires and fears about the future, often through dramatic and imaginative scenarios. Science fiction has long been a source of inspiration for scientific inquiry into faster-than-light travel. Imaginary concepts from novels and films often spark curiosity and drive real-world research into advanced technologies. Many scientific researchers cite science fiction as a catalyst for their interest in exploring new frontiers. Concepts like warp drives and wormholes, initially envisioned in fiction, have become subjects of serious theoretical investigation. Science fiction introduces speculative ideas that push the boundaries of current scientific understanding. These imaginative scenarios challenge scientists to consider what might be possible beyond established theories. The idea of warp drives, popularized by shows like Star Trek, has led to actual scientific discussions about manipulating spacetime. Researchers have explored whether such concepts could be grounded in physical reality, despite the many challenges involved. Similarly, the concept of wormholes, often depicted in sci-fi as shortcuts through spacetime, has prompted serious scientific inquiry. Physicists examine whether such structures could theoretically exist, and how they might be detected or utilized. Science fiction's portrayal of advanced technologies often inspires engineers and scientists to develop new methods and tools. The depiction of futuristic spacecraft and energy sources can stimulate innovative approaches in real-world technology development. The dramatic portrayal of FTL travel in media encourages scientists to think creatively about overcoming the limitations of current technology. It helps to expand the scope of research by framing problems in novel ways. Science fiction scenarios often include advanced propulsion systems that push the boundaries of known physics. This has led to real-world research into alternative propulsion methods and theoretical frameworks. By presenting futuristic technologies and concepts, sci-fi provides a vision of what could be achievable. This vision motivates researchers to explore uncharted scientific territory and develop new theoretical models. The influence of sci-fi on scientific research is not just about the ideas themselves, but also about the enthusiasm they generate. The excitement surrounding these concepts can lead to increased funding and interest in related scientific fields. Science fiction often explores the societal and ethical implications of advanced technologies. This helps researchers consider not only the feasibility of FTL travel, but also its potential impact on humanity and the universe. The speculative nature of sci-fi can also highlight gaps in current scientific knowledge, prompting targeted research efforts. Identifying these gaps can lead to breakthroughs and advancements in understanding complex phenomena. The concept of faster-than-light travel has been explored in various sci-fi works, each adding a unique perspective. This diverse range of ideas provides a rich source of inspiration for scientific inquiry and technological innovation. Sci-fi stories often imagine solutions to challenges that real-world scientists are only beginning to address. These fictional solutions can spark new ideas and approaches to overcoming existing scientific obstacles. While many sci-fi concepts remain speculative, their impact on scientific thought is undeniable. The interplay between fiction and science often leads to unexpected discoveries and new areas of research. The ongoing dialogue between science fiction and scientific research highlights the dynamic relationship between imagination and discovery. Sci-fi continues to inspire scientists to explore new possibilities and challenge conventional wisdom. Particle accelerators have played a crucial role in our understanding of light speed and fundamental physics. By accelerating particles to nearly the speed of light, scientists can observe their behavior and test the limits of relativistic physics. Experiments in particle accelerators, like the Large Hadron Collider, have confirmed the predictions of relativity with remarkable precision. These results help validate that as particles approach light speed, their mass effectively increases and their time dilation becomes significant. One key observation from these experiments is the increase in particle mass at high velocities. This observation aligns with Einstein's theory of relativity, which posits that mass grows with speed and that reaching or exceeding light speed would require infinite energy. Particle accelerators also allow scientists to investigate the behavior of subatomic particles under extreme conditions. These experiments provide insights into how particles interact at velocities close to light speed, shedding light on the nature of space and time. Through collisions of high-energy particles, researchers have been able to create conditions similar to those just after the Big Bang. These conditions allow for the study of fundamental forces and particles, offering a deeper understanding of the universe's origins and structure. Additionally, particle accelerators contribute to the search for new particles and forces beyond the standard model of particle physics. Discoveries such as the Higgs boson were made possible by accelerating particles to nearly the speed of light and analyzing their interactions. The data from these experiments also serve to test theories related to faster-than-light travel. By understanding the limitations and behaviors of particles at relativistic speeds, scientists can better assess the feasibility of hypothetical FTL concepts. Accelerator experiments have provided valuable insights into how particles emit and absorb energy at high velocities. These insights help refine our understanding of energy thresholds and the potential constraints on achieving or surpassing light speed. Research involving neutrinos, which are nearly massless particles, has also offered clues about high-speed physics. Neutrino experiments have tested fundamental assumptions about particle behavior and relativistic effects at extremely high velocities. The observation of particle lifetimes in accelerators has confirmed time dilation effects predicted by relativity. Particles moving close to light speed decay more slowly compared to those at lower velocities, further supporting Einstein's theories. Accelerators have also been used to explore the limits of quantum field theory under relativistic conditions. This research helps clarify the interaction between quantum mechanics and relativity, providing a more comprehensive view of high-speed phenomena. Ongoing advancements in accelerator technology aim to push the boundaries of our understanding even further. Innovations in particle acceleration techniques continue to explore the fundamental properties of matter and energy at extreme velocities. By studying particle collisions and interactions at high speeds, scientists gather data that help refine theoretical models. This process is essential for developing a more accurate picture of how fundamental forces operate under relativistic conditions. Particle accelerator experiments are critical for testing the predictions of relativistic physics in controlled environments. The results obtained contribute to our overall understanding of the universe and the principles governing high-speed travel. The findings from particle accelerators also help scientists assess the practical limitations of reaching light speed. They provide empirical evidence about the challenges and constraints associated with achieving relativistic velocities. Overall, particle accelerators have been instrumental in validating and expanding our knowledge of light speed and relativity. Their contributions continue to shape our understanding of fundamental physics and the potential for future breakthroughs in high-speed travel. Cosmic phenomena offer a unique perspective on the principles of relativity and light speed. Observations of distant galaxies and their light provide empirical evidence for the effects of relativistic speeds on the cosmic scale. The behavior of light from distant supernovae has been instrumental in studying the universe's expansion. These observations help validate the concept of light speed as a universal constant and reveal the vast distances between cosmic objects. Gamma-ray bursts, which are among the most energetic events in the universe, give insights into high-energy physics. These bursts occur in distant galaxies, and their study helps us understand relativistic effects in extreme environments. Astronomers also use observations of cosmic microwave background radiation to study the early universe. This radiation, a remnant from the Big Bang, provides clues about the conditions of the universe when it was extremely young and the role of light speed in its evolution. The study of pulsars, highly magnetized rotating neutron stars, provides valuable data on relativistic effects. Pulsars emit beams of radiation that can be observed from Earth, and their behavior helps test predictions of general relativity and strong gravitational fields. Observations of black holes and their event horizons offer critical insights into how extreme gravitational fields affect light. The bending and redshift of light near these cosmic objects provide experimental confirmation of relativistic theories. The analysis of cosmic rays, high-energy particles from space, also contributes to our understanding of high-speed phenomena. These particles travel close to light speed, and their study helps refine our knowledge of relativistic effects in cosmic environments. Gravitational lensing, where massive objects bend light from more distant sources, is another important observation. This effect confirms predictions made by Einstein's theory of general relativity and provides insights into the nature of spacetime. The study of quasars, extremely luminous and distant objects powered by black holes, helps us understand light speed across vast distances. Observing their light can reveal information about the early universe and the behavior of light over cosmic scales. Cosmic background radiation fluctuations, studied with precision instruments, offer insights into the universe's early moments. These observations help validate the theory of inflation and its implications for light speed and the expansion of the universe. The measurement of redshift in the light from distant galaxies provides information about the universe's expansion rate. This phenomenon helps us understand how light behaves over time and space, reinforcing the constancy of light speed. Observations of neutron stars colliding and the resulting gravitational waves provide another layer of understanding. These collisions offer data on how extreme events impact space-time and light, further validating relativistic theories. The analysis of light from the most distant galaxies and stars allows us to test the limits of our current theories. These observations challenge our understanding of light speed and the structure of the universe at the farthest reaches. The study of variable stars and their light curves provides data on how light behaves in different cosmic environments. This research helps refine our understanding of light speed and its interactions with gravitational fields. Astronomical observations of cosmic structures like galaxy clusters offer insights into the large-scale effects of gravity. These observations help test general relativity and the behavior of light in complex cosmic environments. The exploration of cosmic phenomena helps us test the limits of our theoretical models. Each observation provides new data that challenge our understanding of light speed and relativistic physics. Despite extensive research, tachyons, hypothetical particles that travel faster than light, remain undetected. Various experiments designed to identify these particles have so far failed to provide concrete evidence, casting doubt on their existence. In particle accelerators, no signs of tachyonic particles have been observed. The data collected from high-energy collisions consistently aligns with predictions that do not require faster-than-light particles. Attempts to detect tachyons through cosmic ray studies have also been unsuccessful. These high-energy particles from space have not shown any unusual properties that would suggest the presence of tachyons. Theoretical models predicting tachyons rely on complex and often speculative physics. The lack of empirical evidence for tachyons challenges these models and raises questions about their validity. In laboratory settings, experiments designed to test the properties of potential tachyonic particles have not yielded positive results. The absence of tachyons in these controlled environments adds to the skepticism about their existence. The search for tachyons often involves indirect methods, such as analyzing anomalies in particle behavior. However, these approaches have not led to definitive evidence for tachyon detection. Attempts to use particle detectors to find tachyons have not provided the expected results. The sensitivity of modern detectors has not revealed any signals consistent with the presence of faster-than-light particles. Researchers have explored the possibility of tachyons influencing the behavior of known particles. Despite these investigations, no measurable effects have been detected that would suggest tachyons are interacting with ordinary matter. Theoretical predictions about tachyons include their potential to affect the speed of light. However, experiments aimed at observing such effects have consistently shown results in line with established physical laws, reinforcing the absence of tachyons. In the field of quantum mechanics, tachyon detection has been a topic of interest, but remains elusive. Efforts to identify these particles through quantum experiments have not produced any evidence supporting their existence. The failure to detect tachyons raises questions about the fundamental assumptions underlying their theoretical models. As empirical data continues to be absent, the scientific community remains skeptical of tachyon theories. The lack of tachyon detection impacts the credibility of some advanced theories in physics. Without empirical evidence, many of these theories remain speculative and unvalidated. Attempts to observe tachyons using high-energy physics experiments have consistently fallen short. The expected signatures of these particles have not been observed in any of the conducted experiments. Research into tachyons often involves complex theoretical frameworks that are difficult to test. The absence of experimental evidence challenges the practical applicability of these theoretical models. The search for tachyons has not only been challenging but also controversial. Theoretical predictions have not matched experimental observations, leading to debates within the scientific community. Despite the advancements in technology and experimental methods, tachyons remain undetected. This ongoing issue emphasizes the difficulty in proving the existence of hypothetical faster-than-light particles. The speed of gravity has been a subject of extensive experimental investigation. Researchers have sought to determine if gravity propagates at the same speed as light, which would confirm aspects of general relativity. Experiments using precise measurements of gravitational waves have provided insights into the speed of gravity. Observations from these experiments suggest that gravitational waves travel at the speed of light, aligning with Einstein's predictions. The detection of gravitational waves from colliding black holes and neutron stars has been crucial. These observations have allowed scientists to confirm that gravity propagates at light speed, consistent with general relativity. Astrophysical observations also support the idea that gravity travels at the speed of light. The delay between observing astronomical events and the arrival of gravitational waves matches the expected light speed propagation. Recent experiments using pulsars and their interactions with gravitational waves have reinforced this view. The data suggests that any changes in the gravitational field propagate at the speed of light, as predicted by theory. The verification of gravitational wave speed through LIGO and Virgo collaborations has been instrumental. These experiments have measured the speed of gravity with high precision, matching the speed of light. In addition to direct measurements, indirect methods have also been used to study gravity speed. These methods involve analyzing the timing of cosmic events and comparing them with gravitational wave detections. Comparisons between the speeds of light and gravity have been fundamental in confirming aspects of general relativity. The agreement between the two speeds supports the theoretical framework that underpins modern physics. Experimental challenges include differentiating between the speed of light and gravity in complex systems. However, ongoing advancements in observational techniques continue to refine our understanding of these fundamental speeds. The synchronization of gravitational waves with electromagnetic signals has provided further evidence. These experiments show that changes in the gravitational field travel at the same speed as light, validating theoretical predictions. Research into the speed of gravity involves analyzing data from various sources, including astrophysical observations and laboratory experiments. The consistency across different methods strengthens the conclusion that gravity propagates at light speed. Future experiments aim to improve the precision of measurements related to gravity's speed. Continued research is essential for further confirming and understanding the relationship between gravity and light. The agreement between the speed of light and gravity is a cornerstone of modern physics. This consistency supports the theory of general relativity and helps explain fundamental interactions in the universe. The study of gravity's speed involves sophisticated equipment and methodologies. High-precision instruments like those used in gravitational wave observatories play a crucial role in these investigations. Advancements in technology and observational techniques are continually refining our knowledge. As experiments become more precise, our understanding of gravity's speed relative to light will become even clearer. Dark energy is a mysterious force driving the accelerated expansion of the universe. Its influence on cosmic expansion raises intriguing questions about the nature of space and time. The effects of dark energy on the expansion rate of the universe could have implications for faster-than-light FTL travel. Understanding how dark energy works may offer insights into new ways to manipulate spacetime. If dark energy contributes to the acceleration of cosmic expansion, it could influence theoretical models of FTL travel. This might open up possibilities for new propulsion methods or spacetime manipulation techniques. Research into dark energy focuses on understanding its properties and effects on the universe. This research could potentially intersect with FTL theories, offering new avenues for exploration. The interaction between dark energy and FTL concepts is still largely speculative. However, any advancements in our understanding of dark energy could impact the feasibility of faster-than-light travel. Dark energy is thought to make up about 68% of the universe, yet its nature remains elusive. Its potential role in altering the fabric of space-time could be critical for future FTL technologies. Understanding dark energy might lead to breakthroughs in theoretical physics that impact FTL travel. If dark energy affects space-time geometry, it could provide a foundation for new methods of achieving superluminal speeds. Exploring the relationship between dark energy and FTL travel requires a multidisciplinary approach. Combining cosmology with advanced theoretical models could reveal new possibilities for manipulating spacetime. The study of dark energy involves observing its effects on cosmic structures and the universe's expansion. This knowledge may eventually contribute to developing practical FTL technologies. Theoretical models incorporating dark energy could offer innovative solutions for achieving FTL travel. By exploring how dark energy influences the universe, scientists may uncover new ways to bend spacetime. Dark energy's impact on the universe's expansion could inform theories about spacetime manipulation. Insights gained from dark energy research might lead to practical applications for faster-than-light travel. Future research into dark energy could provide crucial data for refining FTL theories. Discovering how dark energy interacts with spacetime may unlock new possibilities for faster-than-light travel. As we advance our understanding of dark energy, its potential applications in FTL travel become more intriguing. The link between dark energy and spacetime manipulation remains a key area of investigation. The role of dark energy in the universe's expansion poses exciting questions about FTL travel. Continued research may bridge gaps between dark energy, cosmology, and theoretical physics. Exploring dark energy's influence on cosmic acceleration could lead to new insights into FTL travel. Advances in understanding this enigmatic force may reveal novel ways to achieve superluminal speeds. The feasibility of building a warp drive involves significant scientific and engineering challenges. At its core, a warp drive requires manipulating spacetime to achieve faster-than-light travel. One of the primary hurdles is the requirement for exotic matter with negative energy density. This material, if it exists, could theoretically allow for the creation of a warp bubble. Current understanding of physics and technology makes the construction of a warp drive seem highly speculative. The need for advanced materials and energy sources is beyond our current capabilities. A warp drive would require a vast amount of energy, potentially on the order of the mass energy of planets. This immense requirement raises questions about the practicality of such an endeavor. Theoretical models propose that a warp drive could function by contracting space in front of a spacecraft and expanding it behind. This concept challenges our current understanding of energy and spacetime. Researchers are exploring various ways to simulate the conditions required for a warp drive. Experiments and theoretical work continue to assess whether these conditions are achievable. Creating a stable warp bubble involves overcoming numerous scientific obstacles. The energy required and the effects on surrounding spacetime pose major challenges for practical implementation. Advances in quantum physics and general relativity may provide insights into the feasibility of warp drives. New discoveries in these fields could potentially address some of the current limitations. A warp drive's construction would require breakthroughs in both theoretical physics and engineering. Current technology is far from meeting the demands of such a complex system. Efforts to develop a warp drive also involve understanding how to control and sustain a warp bubble. Ensuring stability and safety are critical considerations for any potential design. Theoretical proposals for warp drives are often based on speculative physics, such as hypothetical forms of matter and energy. These ideas require further validation through experiments and observations. Research into warp drive concepts continues, but practical implementation remains uncertain. Scientists and engineers must address fundamental questions about the nature of spacetime and energy. Current experiments and simulations explore whether warp drive concepts are feasible. Advances in technology and theoretical physics could eventually provide answers. Addressing the feasibility of a warp drive involves examining the limits of our current scientific knowledge. Researchers are actively seeking ways to overcome the barriers presented by existing theories. Exploring warp drive possibilities requires interdisciplinary collaboration across physics, engineering, and material science. This approach may help overcome some of the theoretical and practical challenges. While the concept of a warp drive is intriguing, its practical realization remains elusive. Continued research and technological development are essential to move from theoretical concepts to potential reality. Quantum teleportation involves the transfer of quantum information between particles over long distances. This process relies on entanglement, where the quantum states of two particles are interconnected regardless of distance. Recent advancements in quantum teleportation have achieved higher fidelity in transferring information. Researchers have successfully teleported quantum states with increasing accuracy and efficiency. Developments in this field have also improved the distance over which teleportation can occur. Experiments have demonstrated quantum teleportation over distances exceeding several kilometers. Quantum teleportation is not about moving matter itself, but transferring quantum information. This subtle difference is crucial for understanding how teleportation can be applied in practical scenarios. New techniques are being explored to enhance the speed and reliability of quantum teleportation. These include innovations in quantum error correction and entanglement distribution. Researchers are also investigating how to integrate quantum teleportation with quantum computing. This integration could significantly advance the capabilities of quantum networks and communication. Recent breakthroughs include the successful teleportation of more complex quantum states, such as those involving multiple particles. These achievements pave the way for more sophisticated quantum technologies. Advancements in materials and technologies are making it possible to achieve more robust entanglement. This improvement is essential for the practical application of quantum teleportation in future technologies. Quantum teleportation experiments are becoming increasingly sophisticated, with improved control over quantum states. This progress is essential for developing quantum communication networks. Ongoing research is focused on overcoming practical challenges, such as maintaining entanglement over longer distances. Solutions to these challenges could make quantum teleportation more feasible for real-world applications. The development of new quantum teleportation protocols aims to increase the efficiency and scalability of these processes. These protocols could play a key role in the future of quantum computing and communication. Progress in quantum teleportation research also involves better understanding the fundamental principles of quantum mechanics. This understanding helps refine existing theories and models. Innovations in quantum technology, such as advanced photon detectors and entanglement sources, are driving improvements in teleportation. These tools enhance the precision and effectiveness of quantum information transfer. Scientists are exploring potential applications of quantum teleportation in secure communication. Teleportation could enable new methods of transmitting information that are resistant to eavesdropping. The field of quantum teleportation is rapidly evolving, with new findings emerging regularly. Each breakthrough brings us closer to practical applications and deeper insights into quantum phenomena. Recent studies in negative energy manipulation have shown promising theoretical advancements. Researchers are exploring how to harness and control negative energy to potentially enable faster-than-light travel and other exotic phenomena. Experimental setups have demonstrated the ability to generate and measure negative energy densities in controlled environments. These experiments are crucial for understanding how negative energy can be manipulated and utilized. Developments in quantum field theory have provided new insights into the nature of negative energy. This has led to innovative approaches for creating and stabilizing negative energy regions in laboratory conditions. Researchers are investigating the relationship between negative energy and exotic matter. The goal is to determine if negative energy can be used to produce or sustain exotic matter needed for concepts like warp drives. Recent breakthroughs include the successful generation of negative energy in small-scale experiments. These findings offer hope for the practical application of negative energy in advanced technologies. Advanced computational models are being used to simulate the effects of negative energy. These models help predict how negative energy might behave under different conditions and guide experimental efforts. Collaborations between physicists and engineers are pushing the boundaries of negative energy research. These interdisciplinary efforts are essential for translating theoretical discoveries into practical applications. New materials and techniques are being developed to interact with negative energy. These innovations aim to improve the precision and stability of negative energy manipulation in experimental settings. Recent advancements in quantum optics have enabled better control over negative energy states. These improvements are crucial for refining experiments and achieving more accurate results. Researchers are also examining the potential for using negative energy in space propulsion systems. The hope is that manipulating negative energy could lead to breakthroughs in interstellar travel and other space exploration technologies. The exploration of negative energy is revealing new aspects of fundamental physics. This research is challenging existing theories and providing fresh perspectives on the nature of energy and spacetime. Studies are underway to understand the stability of negative energy configurations. Ensuring that these configurations remain stable is essential for practical applications and avoiding potential hazards. Experimental verification of negative energy phenomena is a major focus of current research. Successful experiments could validate theoretical models and pave the way for new technologies. Innovative experimental designs are being tested to enhance the control and measurement of negative energy. These designs aim to overcome previous limitations and achieve more reliable results. The ongoing research into negative energy is attracting interest from various scientific disciplines. This cross-disciplinary approach is fostering new ideas and accelerating progress in the field. Recent theoretical and experimental advancements suggest that negative energy may play a role in future technologies. Continued research is essential for unlocking its full potential and exploring its implications for our understanding of the universe. Fusion power has long been hailed as a potential game-changer for space travel. It offers the promise of providing enormous amounts of energy from relatively small amounts of fuel, which is crucial for long-duration missions. Recent advancements in fusion technology have made it a more viable option for space propulsion. Researchers are focusing on creating stable and sustained fusion reactions to harness this power for spacecraft. In fusion power, hydrogen isotopes such as deuterium and tritium are fused together to release energy. This process mimics the reactions powering the stars, providing a nearly limitless energy source. Developing practical fusion reactors involves overcoming significant engineering challenges. These include achieving the high temperatures and pressures required to maintain a stable fusion reaction. Fusion power could dramatically reduce the travel time to distant planets. With its high energy density, fusion propulsion systems might make interplanetary travel feasible within human lifetimes. The efficiency of fusion reactions could enable spacecraft to travel at a significant fraction of the speed of light. This would drastically shorten the time needed to reach far-off destinations in our solar system. Current fusion research includes experiments with magnetic confinement, such as in tokamaks. These devices aim to contain the hot plasma where fusion occurs, making it possible to sustain the reaction. Another approach being explored is inertial confinement, where powerful lasers compress fuel pellets to achieve the necessary conditions for fusion. Success in this area could lead to compact fusion reactors for space travel. Fusion reactors offer the advantage of producing minimal radioactive waste compared to fission reactors. This makes them a cleaner option for space missions, reducing the environmental impact. Advanced materials and engineering techniques are being developed to handle the extreme conditions inside fusion reactors. These innovations are critical for building reliable and long-lasting fusion propulsion systems. Fusion power has the potential to support large-scale space habitats. By providing a stable energy supply, it could sustain life support systems and other essential functions in long-term space settlements. In addition to propulsion, fusion power could be used for generating electricity in space. This would enable advanced technologies and support scientific research far from Earth. The development of fusion power for space travel is still in its early stages. Continued research and investment are needed to address the remaining technical challenges and bring fusion technology to fruition. Collaboration between governments, private companies, and international organizations is crucial for advancing fusion research. These joint efforts can accelerate progress and make fusion power a reality for space exploration. The successful implementation of fusion power could revolutionize our approach to space travel. It would enable more ambitious missions and open up new possibilities for exploring the cosmos. Developing human FTL travel requires a strategic roadmap that includes foundational research and incremental progress. The first step involves advancing our understanding of theoretical concepts and identifying feasible technologies. Key milestones on this roadmap include creating and testing new propulsion systems that can potentially approach or exceed the speed of light. Scientists and engineers are exploring concepts like warp drives and wormholes to see if they can be practically realized. Investments in advanced computing and simulations are crucial for modeling and predicting the behavior of FTL systems. These tools help in understanding the complex interactions of spacetime and energy requirements. Collaborative efforts between governments, space agencies, and private enterprises are essential for accelerating FTL research. By pooling resources and expertise, we can overcome technical barriers more efficiently. Prototyping and experimental testing will play a significant role in validating FTL technologies. Building and testing small-scale models will provide valuable insights into their feasibility and safety. Public and private funding will drive much of the research and development in this area. Securing investment for ambitious projects is critical for advancing the science and engineering behind FTL travel. Educational initiatives and outreach programs are needed to inspire and train the next generation of scientists and engineers. Cultivating talent and interest in FTL research will ensure a steady flow of innovation. International collaborations could help in sharing knowledge and resources, potentially leading to breakthroughs in FTL technology. Working together on a global scale can amplify progress and address common challenges. Ethical and regulatory frameworks will need to be developed to address the implications of FTL travel. This includes assessing potential impacts on space environments and ensuring responsible use of advanced technologies. Exploratory missions to test FTL concepts in real space environments could follow successful laboratory experiments. These missions would provide practical data on how FTL technologies perform under actual space conditions. Safety protocols and risk management strategies will be essential as we advance towards practical FTL travel. Ensuring that these technologies are safe for human use will be a top priority. Long-term planning will involve creating infrastructure to support FTL travel, such as fueling stations and maintenance facilities. This infrastructure will be crucial for the operational success of future space missions. Public interest and support can drive policy and funding decisions for FTL research. Engaging with the public through education and media can foster a supportive environment for groundbreaking research. The integration of FTL travel into broader space exploration goals will require alignment with current missions and objectives. Coordinating FTL research with other space initiatives will maximize its impact and utility. Regular assessments of progress and adjustments to the roadmap will be necessary to address unforeseen challenges. Flexibility and adaptability will help in navigating the complexities of developing FTL travel. As technology advances, continuous evaluation of ethical, practical, and scientific aspects will shape the future of human FTL exploration. This holistic approach will ensure that the quest for faster-than-light travel remains both ambitious and grounded in reality. In this video, we embarked on a fascinating journey through the world of faster-than-light travel, exploring its theoretical foundations and practical implications. We began by examining the intricate concept of spacetime and how it forms the backdrop for our understanding of FTL travel. From there, we delved into the challenges and potential breakthroughs associated with warp drives and wormholes, shedding light on both the possibilities and limitations of these intriguing concepts. We also explored the hypothetical particles known as tachyons and their role in FTL theories, as well as the implications of quantum entanglement for communication across vast distances. The video covered the ongoing scientific research into FTL travel, including recent advancements and experimental approaches. We discussed the hurdles of negative energy, exotic matter, and how these issues impact our ability to develop practical FTL technologies. The discussion extended to the potential dangers and ethical considerations of manipulating spacetime, highlighting the need for careful planning and responsible development. We reviewed the role of science fiction in inspiring real scientific inquiry and how cultural portrayals of FTL travel influence our understanding and aspirations. Finally, we touched on the roadmap for human exploration of FTL travel, emphasizing the importance of continued research, international collaboration, and public engagement. If you enjoyed this deep dive into the realm of faster-than-light travel, please consider liking the video and subscribing to our channel. Your support helps us continue to bring you intriguing content on the frontiers of science and technology. Be sure to check out the rest of the videos on our channel for more explorations into the wonders of the universe and beyond. Thank you for watching, and we look forward to seeing you in the next video.